Sorry, I'm so sorry. Now it works. Yeah. Thank you very much for joining me today. We should work in a classroom, but we will manage it. At least we should meet maybe each second week, for example. We will fix this, and also if you prefer today to have a classroom, we can just agree on it because I feel it's really important to meet each other. So I will start by. Sorry, I'm so sorry. Now it works. Yeah. Okay. Thank you very much for joining me today. We should work in a classroom, but we will manage it. Okay. Can you see my slides? Okay. So we will start today by just giving an introduction to the course. The course is called Intelligent System, and it's IE 303312. And I have been teaching this course now for maybe 5 years or around 5 years. And this course, it's a really very important course, and it covers many different areas of artificial intelligence. We will also have an introduction to machine learning. We started this last year because I feel that machine learning, maybe it's more important than other parts. So we will try to focus more also this year on machine learning. So maybe we have 12, 13 weeks or 14 weeks. So we will try to give more time to this part. So the course content, the course content, in fact, consists of 4 parts or 4 modules. So the first part, it's an introduction to it's shallow learning or machine learning. You know, in machine learning, we have shallow learning and deep learning. So machine learning, we have shallow learning and machine learning. So in shallow learning, it's techniques which is more simple and it does not require too much computational resources. But in deep learning, it can deal with raw data and it can deal with more complex problems and it can deal with big data. But the problem, it requires very, very huge computational resources. So the first part will be, you can call it machine learning or artificial neural network. The second part, it will be expert system. The third part will be optimization algorithms. And the last part, it will be hybrid system, hybrid intelligent system. So in the shallow learning part or in the machine learning part, we will talk about, in fact, in this, in machine learning, we work with data, correct? So we try to learn from data. So we learn from data. So we need to prepare our data for the learning process. So we will start by data pre-processing. Maybe before also data pre-processing, we need to upload our data to our computer. We need to visualize it. So we need to understand it much better. And after that, we will do some data pre-processing to prepare it for training our models. There are also lots of techniques in data pre-processing. For example, normalizations, scaling, and so on. We will talk about those techniques. Also, we will talk about dimensionality reduction. Dimensionality reduction, it's a technique which is used to simplify my data. So imagine that you have a data set, and in this data set, we have some features. So those features, maybe some of those features are important, maybe some of those features are not important. So we will try to use, for example, principal component analysis for dimensionality reduction. Dimensionality reduction, it simplifies the system, and as I say, simplifies the data. And when we simplify the data, it will be much easier to understand it. It will be much easier also to visualize it. So imagine that you have 4 columns. Those 4 columns, it will be hard to visualize. So maybe you can use principal component analysis to just to simplify it into 2, for example. When it's 2, we can plot it in 2-dimensional space. Maybe 3. And when it's a 3, we can plot it in 3-dimensional space. So it will be much easier for us to visualize the data. And when we visualize it, it will be easy to see different classes. It will be easy to decide what kind of systems we need, what kind of models we need to build to classify this data set. So we will study principal component analysis. And of course, we will talk about, two major approaches in machine learning. It's supervised and unsupervised learning. In supervised learning, we need to have a teaching signal or a target feature. And in unsupervised, we just have input features. So supervised, it's much easier. In fact, it's much easier to understand. In supervised, we have some inputs and we have some output, and we will try to build a system to create a mapping between inputs and outputs. So we call it supervised. In unsupervised, we just have a set of features. So we have a set of features. We don't have any target feature. So don't have any classes. We don't have any labels. So we just try to cluster the data set into a number of clusters. The most important trick here is to decide the number of clusters which you want. For example, we have coins, for example, and a child can do it. For example, if you have a bag of coins, different types, 20 krona, 10 krona, 1 krona, and so on. So, and we need to cluster it, correct? So if you give it to a child and just ask him to order it, for example, or sort it, he will just put things of the same size and the same weight together in one cluster. But maybe he doesn't know that this one it's 20 krona, this one it's 1 krona, this one it's 5 krona, and so on. So this is the clustering. So we try to use some features, and we will use those only features. We don't have any target feature. We don't have any teaching signal, correct? We don't have any labels. So we will just use some features, such as maybe weight of each coin, and maybe also the radius of each coin. So we will just try to make like this. Oh, this is heavy. This one will be 20. This one less, it will be 10. This one will be 5, and so on. Maybe this one, it's much bigger. Radius is much bigger. So this one will be 20. This one little bit smaller, it will be 10. This one will be this one. So in this case, we select some features, and we use those features for clustering the data set which we have. In fact, in unsupervised learning, it's more important than supervised, because when you look around, you can see lots of data sets everywhere, and it's unlabeled. And when it's unlabeled, it's much better to use unsupervised learning to just simplify it, to cluster it. And after that, we will just ask a domain expert, okay, we have 3 clusters. What is this? He will say, okay, this one it's 20 krona, this one it's 10 krona, this one it's 1 krona. So now we finished our problem. And of course, in machine learning, we try to build a model, and this model will be used in the future for solving new problems. So we will build a model. When we give it a new coin, he will decide, okay, this one belongs to this cluster, this one belongs to this cluster. What is the label of this cluster? This one is 20, this one is 10, this one is 1, and so on. So in this case, we solved our problem. So unsupervised learning is really very, very important. And the principal component analysis, in fact, it's one of the techniques of the unsupervised technique. So BCA is unsupervised. So unsupervised is very important, and supervised, of course, is very important, but unsupervised is more important because huge data around us unsupervised. To build your supervised data set, it takes time, correct? So you need to collect your data, you need to decide features, you need a domain expert who will say, okay, this one is cluster 1 or class 1, class 2, class 3. So it takes time to label your data set. But in case of unsupervised, you can just work with the data. We just need to decide how many clusters do we need. Do we need 5 clusters? Do we need 3 clusters? Correct? So this is the only trick in unsupervised learning. When we build a model, we will start with the data pre-processing, maybe dimensionality reductions, and so on. So we will prepare our data. We will agree on the model which we will use for, for example, someone, he will say, okay, I will use a perceptron. Someone else, he said, okay, I will use a feed-forward neural network, and I will start to training it. When we train our data, our model, I have a bunch of data. I have a bag of data. This bag of data, I cannot use it all for training my model, correct? I need to divide it into one portion for training and one portion maybe for validation, one portion for testing. And it's important because when you train a model, you need to test it. So if you are working in your office, for example, you build a model for a company, you need to test it and validate it before deploying it in real life, because no one knows if it is really good or bad, right? So in this case, how can we test it? So if you have bag of data, you need to divide it into small sections, and you just need to keep one section for training. Maybe this is the largest section, and a smaller one for validation, and a smaller one for testing. This is very, very important. And the one for testing, we will just keep it away. We will put it away because I don't need my system to know anything about it. It's like an exam. So during the whole semester, you have a book, you study from this book, and at the end, you will have few pages, some questions for testing, correct? At the end, you don't have the book anymore. And we cannot give you the exam from the early week in the course, because maybe you will just go to those questions, you will try to find those answers, and you will just memorize it, and you will get 100%, correct? You will get A. But in fact, in this case, this person does not deserve to get A, in fact, because we have some information leak now. He got the questions, he tried to just study those questions, and he got A. But maybe he got A without, understanding the concept of the course and so on. So when we need to prepare a test, we need to keep the test away just for testing at the end. So after training the model and validating it, we just need to test the model accuracy. This is very important. We need to check the accuracy of the model. So, so when we divide the data into training, validations, and testing, we need also to check the performance in training and the performance in testing. Because if the model was fantastic in training and his performance is really bad in testing, it gives us impression that, okay, my model has a problem, my model has memorized my data set and it cannot generalize. And in this case, we call it overfitting. So we have overfitting problem. So this is really very, very important. So even when we divide the data into some sections, one section for training, one section for validation, one section for testing. Of course, the testing part, it's very important because it will test the final model. So I trained my model, I fine-tuned my model, and I will use the testing data set for evaluating the final product. So I can just say, okay, this model has accuracy 80%, this one has accuracy 85%, which is really very good. So in fact, we use a testing data set for testing the final product, the final model. But we still have some problem also. I need to know the performance in training and the performance in testing and to compare those two numbers together. Comparing those two numbers together, it will help us to understand to identify if the system has a problem of, for example, overfitting problem or underfitting problem. And we will talk about this more in details when we start playing with examples. In that part, we will start with a simple model. This simple model, it is a perceptron. And the perceptron, it is a basic computing unit in artificial neural network. In fact, artificial neural network, it consists of layers of nodes. Those nodes are perceptrons. So the perceptron, it is a basic computing unit. We will start with this one. The basic calculating unit, it can generate a decision line, and this decision line can be used to divide two different data sets into two classes, for example. So the perceptron is very, very important, and we will learn how to use the perceptron for solving simple problems. Yes, we can use a perceptron for solving simple problems, but when the problem is really very complex, what does it mean complex? It means I have two classes, maybe those two classes have some kind of overlap. So in this case, the decision boundary will be very complex. It will be very complex for a perceptron to solve. And in this case, we need to connect several perceptrons together and arrange those perceptrons on layers and use this one, we will call it feed-forward neural network, and we will use this one for training this complex data set. So a perceptron can be used for solving simple problems. We call it linearly separable problems. But at some point, we will see that, okay, it's impossible to solve because, in fact, each perceptron generates a decision line. So maybe in some data sets, it's impossible to solve with a single decision line. So in this case, we need to use something else. In this case, we need maybe to connect two perceptrons together, maybe connect three perceptrons, because when you increase the number of parameters, because the perceptrons, each perceptron has weights and bias. Each perceptron has weights and bias. Maybe I will give you an example. I have a data set, and the data set has two inputs. So in this case, the perceptron has three parameters, two weights and one bias. So maybe two weights and one bias, three parameters. So this is a degree of freedom which we have. So in fact, I play with three parameters. I'll play with three parameters to try to generate a decision line to solve a problem. If the problem cannot be solved with one perceptron, it means that no, we need to add more parameters. So I can add more perceptron. If you add another perceptron, you will have 6. If you add another one, you will have 9. And when you increase the number of parameters, your capability for solving complex problems will be much, much easier. So we will start with a perceptron, and after that, we will also study something called the perceptron learning rule, because the perceptron has some number of parameters. Those number of parameters, maybe we can visualize the data, or we can try to find the weights and the bias by trial and error. But instead, we can also learn a learning algorithm. This learning algorithm called perceptron learning rule, and we will use this perceptron learning rule to train a perceptron for solving a problem. So in fact, all what we need is data, right? Data, and you need to decide what model you want to use, and the optimizer. The optimizer, we call it perceptron learning rule. The perceptron learning rule, it's just one code, one line, which will be used for adjusting the weights. In fact, it will select a combination of weights which will minimize the difference between the predictions and the target output. So because my data set, it has some features, some inputs and some output, I will use a perceptron to solve these problems. In this case, we will use perceptron learning rule to try to minimize, to find a good selection or good combination of weights and the perceptron to solve the problem. When the problem is really very complex, we cannot use a perceptron anymore. And in this case, we will just connect a number of perceptrons together. And there is no reason. It's just we need to increase the number of parameters. And when you increase the number of parameters, your ability, your capacity to solve more complex problems will be much, much higher. So in fact, we can say that at the end, machine learning, it's an algorithm which has a bunch of parameters. It has lots of parameters. And we need to find a good combination of those parameters to solve a problem. And I know someone who was working in artificial intelligence a long time before, and he just said, if you have a neural network, you can just, you can just use it to plot an elephant, for example. So just to change the combinations of the parameters of your neural network to plot or draw an elephant. So when perceptron cannot help us for solving some kind of problems, we will try to build an artificial neural network. A neural network, it's just a collection of those perceptrons. And those collection of perceptrons are organized in layers. So we will put them in layers. Why it's in layers? It's just to make life easy for us for calculations. But it's up to you to find any configuration for it. So the artificial neural network, in fact, it's just a number of perceptrons connected together in layers to make calculations easy. And we will see that we will see this in, when we go forward. When it's in layers, it will be easy for calculations. We can just switch into matrix multiplications, because in artificial neural network, we will go forward for calculating the outputs. And after that, we will calculate errors, and we will go backward to adjust our weights. So in this case, when it's organized in those layers, it will be easy for calculations. We can just use matrix multiplications for speeding up the process. So we will talk also about something called transfer learning. And the transfer learning, it's, when we need to train an artificial neural network, we need data, correct? So, and if your problem is complex, you really need large set of data, right? So it's a problem. So when I need to train an artificial neural network, I need data. And if the problem is really very complex, I need large data, a larger neural network. So I need to construct a complex artificial neural network. And also I need, when it's complex, I need more data to train those parameters. Because when it's a large neural network, we will have huge number of parameters. And to train those number of parameters, you need a larger amount of data. So transfer learning, in fact, it's an idea which comes from this domain. So for example, some companies, they have huge resources. They have lots of data. They have also computational resources, very high computational resources. So they are more capable than us in this domain. So they can build models for solving very, very complex problems, for solving any problems. Maybe it's machine vision problem or whatever, and they put it in public. So in this case, we can borrow this artificial neural network, and we can try to modify it and use it for solving other problems. And in this case, we don't need, in fact, it's more famous in deep learning. So in this case, I will borrow this artificial neural network, which has been used for maybe image classification, and I will use it for solving any other problem like handwritten digit classification, for example. So it will save time because I can just change maybe the last layer of this neural network, which is in charge of decision making, and I will retrain only the last layer for using my small data set, and that is it. And it will give us very good results. So to train an artificial neural network, we need an optimizer. The optimizer in this case will be error bag propagation. So error bag propagation, and the error bag propagation, in fact, it's a gradient descent algorithm. So we use gradient descent. During the course, we will use some benchmark problems. And yeah, I have some questions. Yes. Yes. Any question, please? No. Domain expert, it's a human. Yeah, correct. Domain expert is a human, right? Not a machine. We will go. In the next section, we will talk about expert system. So in fact, the domain expert, usually we call it a human. Maybe if you are working in a medical problem, maybe you need a doctor to help you. So he will be the domain expert. If I'm working, for example, in building a system to deal with all the people in a nursing home, for example, so I need a domain expert. Maybe a domain expert will be a nurse because she has knowledge, or he has knowledge from this domain. So I guess they will help us to understand. For example, we call in banking, for example, if you are working in a bank, or if you try to build a system to classify who should get a loan, who should not get a loan, right? So we will collect the data from the bank. We need a domain expert from the bank also to help us to understand the system, right? He will help us to understand what does this variable mean and so on. So it's very important to have a domain expert when you are working in machine learning. Yeah. Yes. So during this course, we will work with some benchmark problems and real world data sets. It's a simple data sets like MNIST data set, Olfiti data set, IRIS data set, and you are welcome if you have a problem. You can just try to collect a data set, or you can just bring your own data set to the classroom, and you can work on it. So we will try to work with time series, also object recognition, face recognition, predictions, classifications, regression. So in fact, we will try to cover all different types of problems in machine learning. So the first part, in fact, I'm expecting it to take more time, because if we need to go deeply into it, it will take much more time. And this part is really very, very important, because maybe in your project next semester, you need to apply some of those machine learning applications or models for solving your problems. And last year, for example, we had lots of students who has been developing models for fish classification, for example, right? So they want to classify fish according to the size. They want to find fish with problems, with cuts, without tail, without some parts, for example. So the whole problem is just collect your data set and try to build your machine learning models. And the last year also, I noticed that many people used deep learning. So from bachelor also, so they use deep learning. So the knowledge which you will get during this part, I guess it will be helpful for you, even to use some deep learning models next semester. You can use those deep learning models as a black box, but also, during this course, you will understand the basic concept of deep learning. The second part of the course, we will talk about expert system. And expert system, it's different from machine learning. Machine learning, we are working with data, correct? So if I want to solve a problem for the bank, for example, I just need an Excel sheet from the bank. So I don't need the customer names, but I need transactions, assets, age, jobs, and so on. I need features. So I need just an Excel file from the bank, which contains information about customers, right? And I will use this information or this data for building a model which will classify them into maybe who should get the loan, who should not get the loan, and even also predict how much loan he should get based on his income, his age, gender, and so on. And you cannot imagine, I mean, in banks, they use also, if you have a Facebook account, if you have a Twitter account, if you have, I mean, they use lots of information, in fact, which without, consent from customers. So they search for many things. They have algorithms, and those algorithms are looking for too much information which you cannot imagine. And they use all those informations to make a decision, yes or no. Should we give him a loan or not? So the most important part here is data collection, because in machine learning, we work with data, we learn from data. But in expert system, we learn from human, in fact. In expert system, I want to build an expert system for solving a similar problem. For example, I have a data set which called dogs and cats. So dogs and cats, it's images. So maybe I have 200 images, 100 for dogs, 100 for different types of cats, correct? And I want to build a machine learning model for solving this problem. So the domain expert here, which we have been talking about, he will just label it. He will look into it. Okay, this one looks a cat, this one looks a dog here. So he will label my data set. So in this case, I will have set of images, and I will have also labels associated with it. So the domain expert here, in fact, he will help us to annotate those images. He will say, okay, this one is cat, this one is dog, this one is cat, this one is dog, right? So in fact, he helped us to label the data set. And after that, I can build a deep learning model or an artificial neural network, which will use the image, maybe pixel by pixel, or maybe extracting some feature from each image. And I will try to build a system to help us to make those decisions. And dogs and the cats, it's two classes, correct? So we have two classes. So we can plot it in two-dimensional space. Those images are for cat, those images are for dog, and we will build a system. But in expert system, maybe, for example, if we can talk about income, you want to get a loan from the bank, for example. So they will say, if your income is greater than this number, you can get a loan. If your age below this number, you can get a loan, correct? So for example, your income, if you earn more than $500,000 per year, for example, you can get a loan. If you are younger than maybe 65 years or 50 years, you can get a loan, and so on, right? So in fact, in the expert system, we try to ask domain expert how we try to notice how they solve a problem, and we try to extract this knowledge from the domain expert and implement it in this expert system as a set of fuzzy rules or if-then rules. It's just if-then rules. So we have a set of if-then rules, and we will create a set of if-then rules. We call it role base. So the role base will be will help us to make decisions. We will have a rule base. Maybe the rule base has 10 if-then rules. So we will use those 10 if-then rules for solving the problem. But we will ask the domain expert, how do you solve it? And we will try to break it down, because the decision making, it's a very complex problem. But we will try to break it down into small pieces. Each piece will be if-then rule. So the rule base, in fact, here consists of rules, and each rule is if-then statement, correct? And your system will be smarter if you have more rules, correct? If you have very simple rules, it will be easy. So for example, I just have this one. Okay, this one, it looks like, I don't know, you just need to find an example. So maybe if this one is black, maybe it's a mobile. If this one is black, it's a keyboard. If this one is larger than this one, it's a keyboard. If this one is smaller, right? If this one makes a sound, it's a mobile phone. If this one does not make sound, maybe it's a keyboard, and so on. So in fact, you need to ask him, you need to notice how he solved a problem, and you need to try to extract this knowledge from him and try to break it down into rules. And those rules will construct a rule base, and this rule base will be used for solving our system, our problem. And this we call it rule-based system, right? Rule-based system, because it's based on rules. And so the rule here, in fact, it will be the basic building block of an expert system. So this if-then statement, it will be the basic building block of our system, and it's a piece of information which will be used here. So if we need to compare it to shallow learning, for example, I can just say, okay, a rule is equivalent to a perceptron, because the perceptron, it is a basic building block in artificial neural network. So in expert systems, the rule, it is a basic building block also. So this is a piece of information which we will use. And my system will be smarter. My system will be able to make more complex decisions if I have a huge number of rules. So maybe my system has 50, your system has 150. So I'm expecting that your system will perform much better than mine, correct? But also we need someone called information engineer. So this one will be, will try to extract this knowledge from the domain expert and write it down as a set of rules. This is very, very important. In expert system also, because if you go to the bank, maybe you can find, for example, in the bank in Olufsen, they have a famous guy. He will get retired very soon, but he is really very smart. He is old. He has huge experience. So you will get some knowledge from him. And he is very good. He just look into your application and he just decide, okay, you should get a loan. This one should not get a loan. Because this is very, very complex problem for the bank. Because if I deserve it to get a loan, and the bank said no, they will lose a customer, correct? And if I should not get a loan and they said yes, so they will lose money, correct? So, and they will be in, I mean, it will be a long process, in fact, and it's a problem if you can get a loan and if you cannot pay back. But by the way, people who are not paying it back to the bank, they are, bank get more benefits from those who don't pay, in fact. So anyway, so if we are building this rule-based system, we need a domain expert, and the domain expert will help us to get those knowledge. So maybe we have one who is more expert than another one. So in this case, I will get if then statement from someone who I trust in his knowledge, and I got also a set of rules from someone else who he is okay, but I don't trust him very much because he is still in his career. He's just started his career maybe some years before, so he has knowledge, but it's not very deep knowledge. So in this case also, we need to differentiate between rules. A rule which we got from one who is really expert, and rules which we got from someone who is not really expert in his domain. So in this case, we need to differentiate because all those rules, we need all those rules to contribute to the decision making, but also the amount of contribution, it will be based on the amount of trust which we put. So we can assign a weight value to each rule. So I have a set of rules, maybe I have 20 rules. So some rules will have a weight value of 1, some rules will have a weight value of 0.5, another rule will have a weight value of maybe 0.1, for example. So some rules will contribute by 10%, some rules will contribute by 100%, some rules will contribute by 50% to the decision making at the end. And this is very correct, because if you create a group, for example, and we are just sitting together and discussing, and we want to make a decision, correct? So usually, I mean, people just give more weight to the one who has more knowledge in this domain. So it's very democratic, in fact. In these systems, we have something called type 1 and type 2. We will implement it using fuzzy logic system because it's very easy to implement. And in fuzzy logic system, we have fuzzy sets, and those fuzzy sets, we have two types, one called type 1 and one called type 2. Type 1, it's very simple. Type 2, it has a width, and this width can be used to consider uncertainty in my knowledge. We will talk about it later on. We have also a benchmark problem. It's a mortgage example. We have an example from a bank, in fact, and we will use this example as a benchmark problem. We will try to implement it. So in fact, maybe we can pick a problem. Maybe we can solve it using shallow learning, and also solve it using an expert system, and make comparison at the end. Which one is better? Which one is good? Which one is bad? Right? The difference between machine learning and expert system, it's learning from data, correct? So once we have more data, we can just train our model and retrain, right? So for example, for the same problem, I get data sets from different set of banks, and I want to build a model for this, loan stuff, for example. So I will build the system and I will start using it. And maybe next year we got new data files from Oslo, from Bergen, from whatever. So I will use those data to retrain my model. So you can just retrain your model at any point. And this is very flexible, in fact. So at any point, if you got new data, You can just use those new data for data sets for retraining your model and just use it. So your system will be easy to update your system, in fact, much easier. But in case of expert system, it's a problem because it's rule-based system, so it's based on rules. So once we build it, we have to use it, because if you need to update it, you need to go to those rules, you need to remove some rules, you need to add some rules, you need to increase the weight value of some of those rules, you need to decrease the weight value of some of those rules, which is really very complex. And it's also very hard. So when the number of rules increases, so imagine that you have a system which has 10,000 rules. It will be really very complex to know which one is doing what, because it will be very hard for us to update our system using new rules, because the system really will be very, very complex to understand and to know which one is contributing, which one is not contributing. So working with machine learning, it's much easier, more flexible. You can train it at any point in the future. So it can learn. So they call it, it can learn. Machine learning, it can learn. But expert system, it cannot learn. Once we build it, it will stay as it is. So if we build a system from 10 years, so imagine that we are building an expert system for banks in Oluson, and we got those rule-based from people who have been working in 1980, for example. We cannot use the system today, correct? Because on those rule-based, he will say that, okay, at 1980, for example, if your income is less than 50,000 per year, you will get a loan. So in this case, if we use the same rules today, all people will get loans from the bank, and maybe not all of them will be able to pay back, right? So you need to update your system, and updating it will be very expensive, especially if it has really many rules. And also it's a problem because it's based on human. So maybe I used some people, and those people does not exist anymore. Maybe they got retired, whatever. So because the source of information in expert system, it's a human. It's based on human experience. So if I don't have access to those people who helped us to give us those rules, it will be a problem. Another problem also, some people, they make decisions, but they don't understand how they make it, correct? So some people solve the problems, but when you ask him, how did you make it? You just say, it's my by intuitions. Or so some people, it's really hard to know how they make decisions. But when you are working with data, we don't care. We have Excel files, we have data files. We collect those data. We collect those data from Bergen, from Trondheim, from Oslo. So at the end, we can have a universal system which can be used on Ålesund, which can be used in Bergen, which can be used in Trondheim, which can be used, for example, in Oslo at the same time. Because I keep updating my systems with new data. And even you can sell your system to other country. You can just build the system and sell it to another country. They will update the system using their own data sets and customize it for their case. But if you build a system here, for example, imagine I'm building air conditioner, for example, using an expert system. So I build an expert system for controlling the air conditioner. If I build it in Ålesund, I cannot use it in South Africa because the temperature is different. The feeling of people is different. Maybe when it's 20 in Ålesund, it's hot. When it's 45 in South Africa, for example, this is hot, correct? So if you need to build an expert system, it's a problem because updating it's very expensive. And even they said that it's much cheaper for us to rebuild a system from scratch instead of updating an old system. But we have very good advantage of expert system. Expert system, it's a transparent system, right? So I know that there are set of rules, and when those rules are used for decision making, I can find which rule will be fired, right? Because some of those rules, imagine that I have 20 rules covering range of inputs. So we have those set of rules covering number of features, a range of inputs, and then when we apply it, some of those rules will be fired, some of those rules will not be fired. So I can trace which one is fired, which one is not fired, and I can understand how the decision has been taken, in fact. So it's a transparent system. So it's they call it white box system. It's white box. Why it's white box? Because they can look into it and I can understand how the decision has been taken by looking into the set of rules which has been fired. So this rule has been fired first. This rule. Maybe between 20 rules, I have 10 fired. So in this case, you can understand that you can explain why we had taken this decision. So if you have a customer in a bank and he applied for a loan and told him, no, you cannot get a loan. Maybe he need to ask why I shouldn't get a loan. I provided all informations, my income, my age, all those informations, assets, and so on. So why I shouldn't get a loan? So you can go to your system and you can get the set of rules which has been fired, and you can explain to him, yeah, because you can trace back. In fact, we can trace back from output to input. You can say, okay, it's because maybe you have this one here, your assets, your income is not that much. So you can explain to him why we have taken this decision. But in case of machine learning, it's impossible, because machine learning, as I told you, when it's a perceptron, it's easy to understand, right? Because when you have a single perceptron and 2 inputs, it's easy. But when it's an artificial neural network which has 20 inputs and 5 layers, for example, and 10 outputs, it will be impossible for us to understand anything. When you look into the artificial neural network, you will just see numbers. Those numbers does not have any meaning, in fact. It has meaning for the problem which we are solving, but if you want to explain to the user, for example, why we have taken this decision, it's impossible to understand it. So even in dogs and cats, so you have dogs and cats, and you just classify it into dogs and cats. You cannot explain to him why. I don't know. We trained the system, we adjusted the weights in a way to solve this problem, but the system is really very complex and it's hard to explain to the users what has been done. So artificial neural network, it's black box models, but expert system, it's white box model. Did you hear about transparent intelligence? Transparent intelligence, it's a way for building systems which help people to just explain decisions. Why you have been taking this decision. So imagine you build a system for diagnosis, medical diagnosis. So you collect X-ray and MRI images, blood pressures and blood analysis, and so you collect a bunch of data. You feed those data to the system, and the system will say, okay, we predict that maybe this patient will get a kind of disease in the near future, or he got this one already. If he asked you to explain, it will be impossible to explain him what has been done. So those black box models, they are very good, very efficient, fast. You can update it at any time. It can learn from data, but it has this problem. It's not transparent. It's a black box model, so it's impossible to understand or explain why such decisions has been taken. But in case of expert system, it's much easier because we can trace back. We can trace which rules has been fired, and we can explain why the decision has been taken. So the third part of the course, it will be optimization algorithms. And in this optimization algorithms, it's very, very important also. We will cover 2 optimization problems. The first one, it's a single objective optimization problem. And the second one, it's multi-objective optimization problems. Single objective optimization problems, it's just the objective function here. We have an objective function which we need to minimize, right? We have a single objective function which we need to minimize. So imagine I want to travel to Oslo, for example, and I want to minimize cost. So I have some decision variable. So the decision variable may be transportation way. I need to move from Ålesund to Oslo, and I need to select transportation approach or transportation way, for example. Should I go by car? Should I go by camel? Should I go by fly? Should I go by bike? Right? Should I go walking? So maybe you can just say, okay, I need to minimize cost. I need to pay 0, correct? So maybe in this case, I can go by bike because I don't care about time. I just care about cost. So I will just go biking, right? So in this case, we have a single objective, which is the cost, which I need to minimize, regardless of anything else. So this is a single objective optimization problems. But the same problem, we can formulate it as a multi-objective. So it's the same problem. I want to travel from Ålesund to Oslo, but I need to minimize cost and I need to minimize time, right? So I need to minimize cost and I need to minimize time. So if I selected, for example, walking, right? So time will be very huge. It will take some days. It will be maybe 6, 7, 8 weeks, maybe a week, for example, of walking, or I don't know, and maybe you know better than me, but maybe it will take 6 days walking, for example. So in this case, I cannot use this option, right? Maybe I can go by bike. If I will go by bike, maybe it will take 2 days or 3 days biking. maybe. So in this case, it's much better because the cost is less, but I bought a bike, so I paid little bit, but at the same time also, the time is much better. So instead of arriving in 2 weeks, I can arrive in 3 days, for example. So the other option, maybe you can say, okay, I can go by train. If I go by train, maybe it will take maybe 6 hours or 7 hours. I need to pay the train ticket, which cost maybe 1,000, right? Maybe someone else, he would say, no, time is more important for me. In fact, time is more important. I want to arrive in 30 minutes. And in this case, I will fly, right? So in this case, I will pay maybe 3,000, but I will arrive in 30 minutes. So in this case, this multi-objective, we have cost functions which are competing with each other. I have two cost functions here. I have the cost and I have the time. I need to minimize time and I need to minimize the cost. So we have two objective functions which are competing with each other. And in this case, as I told you, we will provide a set of solutions. I will provide a set of answers. You can go by bikes, and in this case, you will the cost will be maybe 1,000 for cost. I mean, if you want to buy a bike, for example, or rent a bike, or if you have already a bike, and the time will be, for example, maybe 3 days. If you want to go by airplane, in this case, you will pay maybe 4,000, but you will arrive in 30 minutes. So you can just select. So in fact, all objective functions must be multi-objective optimization problems. But when we study this optimization algorithms, we will study how can we convert multi-objective optimization problem into a single objective optimization problem. So because we can combine those multi-objectives into a single objective. So it's one way for solving it, but also we can solve a multi-objective optimization problem in a way to give you a set of solutions, a set of solutions. We call it Pareto set. So this part also is very, very important, very, very important. And at the end, if we have enough time, we will study hybrid systems. And this hybrid system, if you look above, we have machine learning part, we have an expert system part, we have optimization algorithm. So we will try to build a hybrid system between from those systems. So maybe we can combine machine learning with expert system, right? Maybe we can combine optimization algorithm with artificial neural network, because in artificial neural network, we have, we have hybrid parameters. Those hybrid parameters, how can we select it? We don't know, in fact. It's by trial and error, or by experience, or by chance. I mean, there is no rule for anything, in fact. So instead of selecting those hybrid parameters by yourself, maybe we can use an optimization algorithm to help us to find the best combinations of those parameters. So in this case, we can use, for example, optimization algorithm, maybe genetic algorithm with artificial neural network to select number of hidden layers, number of nodes in each hidden layer, and so on. So we will try to mix those algorithms to improve performance, automate selection of hyperparameters, and rid of cons of such some of those systems. So if we combine an expert system with artificial neural network, for example, maybe we can build an expert system which can learn from data, correct? We know machine learning, it can learn from data. This one, it cannot learn from data. So if we can combine expert system with artificial neural network, maybe we can build a system which is transparent, because I know that the advantage of this system is it's transparent, it's white box. Disadvantage of the system, it's black box, correct? So maybe if we can combine this one with this one, can build an expert system which can learn from data, correct? Which is really very good achievement, because I can build a system which is transparent and at the same time it can learn from data. We will take break soon, but we have this introduction finished. Do you like to have a break, or should we continue? Hello, guys. Can you please say something? Okay, so we will take. Okay, very good. Okay, great. So we will take a break, but also please just open your mic and just say anything. So if you have any questions, for example, just inform me. If we need to go into details, I mean, this is the first time to teach without Blackboard. So we will see if it will be okay today. Otherwise, we will search for a good place next week, and we can have a classroom. So we will meet. Just drink your coffee. Maybe we can meet after 10 minutes, for example, or 12 minutes. So we can meet at 11:20. Yeah. So we will have a break now. Thank you very much. Hello, everybody. So we will go back again to the slides. I mean, this time it will be much. Okay. So yes. So the course material, you have this link, which is it is a link for the course for the subject at NTNU website. So, and it has some information about the exam, about home assignments, and so on. We will have 3 home assignments, and we will have oral exam at the end. This is the Blackboard, and when you log into the Blackboard, you will see some folders. One folder for lectures, one folder for code, videos. I will upload recording of each lecture into this folder. And also, if we have some data sets, we will upload the data sets here. GitHub page, I just created this GitHub page, in fact, this year, and I wish that when we are working in a problem and when we are happy with it, we can just upload some answers to GitHub. So other people can just, so in fact, it's just a way to share the code with the rest of the classroom, and maybe also for the next years when we are teaching this course again, so people can just use some of those codes. So we will start working with some problems, and when we are happy with it, we can just upload it to GitHub. Data sets, it's a problem. It's not a problem. In fact, there are lots of data sets around us everywhere. So we can get data sets from Kaggle, for example, and we can get data sets also from UCI machine learning repository. This one is very, I mean, we used it several times and we use this one a lot. So just select any data set and you can start playing with it. So we have also some benchmark problems in the book we will use. We will use some data sets from last year, like MNIST and 50 data sets, but also time series, any data sets for time series and so on. So if you wish, you can just find any good data sets and you can just ask me, or you can just upload it directly to this folder. So all of us can use it and play with it. The book, we use this book, in fact, but we are not covering all chapters. So we will just go to some chapters, and I uploaded to Blackboard also the course plan, and I will show it to you, so you can know which chapters we will focus on. So this book is a nice book, and we have been using it for, I mean, many years now. Maybe we need to update it or select a different book, but this book is still okay. For coding, some of you will use Python. I wish if you will use Python, you can just use Google Colab. And some of you, of course, especially people came from automations, they will use MATLAB. So it's fine for coding. Google Colab, we use it in another course. In fact, I'm using this Google Colab in machine learning in the master. And it's nice because it has a GPU. It's a free and open source environment for Python development. And it requires no setup and runs entirely on the cloud. So this tool is really very good. You can use it for Python programming. And it's a Google version of Jupyter Notebook, and it contains all the pre-installed packages. So it has all, I mean, in machine learning, there are lots of packages which make life much easier, such as Keras, for example, TensorFlow, PyTorch, and so on. So those packages are already installed. So you can just write your code directly and work with it. You don't need to install anything. So just you can also develop deep learning applications on the GPU for free. So this one has Tesla K80 GPU. So you can just use it for free. So using a Google Colab, in fact, it's very good. And we can share our code with the rest of the classroom easily. This is an introduction to Colab. So I wish that you can go to this one and try. I mean, maybe we can take a break after 1 hour and try to go to Colab and just get started. Try to write your Hello World program. So we have some data sets. I can just upload this data set to Blackboard. We have 2 small data sets, and you can just upload those data sets and try to visualize it. If you will be working in Python, you can do the same also if you will be working in MATLAB. So we will take some exercise in Colab. We have a small data set. It's called the salary data set, and it's for regression. You know, in machine learning, we can build models to regress, and we can build the models to classify, we can build the models to cluster, right? So this salary data set, it's for regression, and it consists of two variables, an independent variable, which is number of years of experience, and a dependent variable, which is annual salary. So in fact, the data set consists of two columns. One column is the number of years of experience, and the other one is the annual income or salary. And of course, it's not covering all. I mean, in the x-axis, for example, we have years of experience, and in the y-axis, we have the salary. So in the x-axis, it started from maybe 0 to 10, from 0 year to 10 years, and it's not covering all years. So it's this kind of problem. It's a regression problem. It's important to find a regression line which fits my data, so we can use this regression line to find in between values, right? So maybe I have been working for maybe 5 years and a half, and in the data set you cannot find 5 years and a half. So when you have a regression line, you can make interpolation, right? You can make a kind of interpolation, and you can find how much salary we should expect after 5 years and a half. So this data set, it's very simple, and as an example, I can just upload an example, but I want to leave you to work with it a little bit. So first, you need to upload the data set to Colab and try to visualize it. And also, if you can build a simple regression model, it will be okay. The regression model, it's very simple. Regression model, it's y equal mx plus c, correct? Y equal mx plus c. M is the slope of the line, and the c is the intersection with the y-axis. So when you plot the data, you will see how the line should look like. And the idea here is to find the two variables. Two variables here, unknown variables, are the slope of the line and the intersection with the y-axis. So if you can find m and c, it means that we can find the parameters of the regression model, and we can use this regression model for predicting, right? Beyond the values which we have. So I have number of years of experience. Maybe it's from 0 to 10. But what happened? What if 12? What if someone has been working for 12 years? So we should be able to use this line to predict how much he will get, for example, after 2 years, for example, using this regression line. So you need to upload the data to Colab, visualize it, and try to find a regression model to fit the data. So we can use this regression model to predict annual salary in the future, for example. Correct? So we have also another example. So the other example here, it's MNIST dataset. You can download it from UCI repository. And the MNIST dataset, it has been collected by Fisher in 1936. And this is the data, in fact, this table. So in fact, it's 5 columns, A, B, C, and D. A, B, and C, and D, it's Sebel length, width, beta length, and width, and E, it's the classes. So in fact, we have 5 column matrix. You can just say it's a matrix consists of 5 columns. The first 4 columns are the target, the input features. So A, B, C, and D, we call it input features, and the last column here we call it target feature. So we have classes. So in fact, they just measure. For each type of flower, they measure the width of sepal and petal, and they try to classify it. We have 3 classes: versicolor, Setosa, and virginica. So we have 3 types. So using those features, we should be able to classify it. So when you measure the length and width of sepal and petal, you can classify your flower into 3 classes. So this data set, it's nice. So this data set, it's for regression, right? It's a very simple one, regression. It's like a time series. We need to regress. And this time series, it's for classification. Why it's a classification? Because we have a target feature here. We have this column. So this column will be like the target signal, the signal which will help my model to learn how to map inputs into outputs. We have outputs. But of course, we can solve this problem as unsupervised. But we just need some knowledge. What knowledge? I know maybe this data set, it's 3 clusters, so we can classify it into 3 clusters. correct? So in fact, we can solve this problem as a supervised or as an unsupervised. When it's unsupervised, we will cluster it. We cannot say that we are classifying. No, we're clustering. But how many clusters? So you need to decide how many clusters. Should we cluster it into 2, into 3, for example? Because it's up to us. I can make it 2 clusters, and I can make it 3 clusters, 4 clusters, 5 clusters. So we need some domain knowledge here. So the domain knowledge, maybe people who are working in this domain knows. You can just say this. So iris flower, it's only 3 clusters, 3 types. So with little domain knowledge, we can say, okay, we need to cluster this one into 3 clusters, and after clustering it, we will ask a domain knowledge who will look into each cluster, and he will say, okay, this cluster is versicolor. This cluster is Setosa. This cluster is Virginica, correct? So after solving the problem as an unsupervised problem, we need a domain expert who will help us to just give a label. Give a label to each cluster. We will solve it. So in this case, we will just use those 4 columns. We will use the features for solving this problem, and we will cluster it into 3 unknown clusters, but we need a domain knowledge, a domain expert to give a label for each cluster. It's like coins. As I told you, it's the same like coins problem. Each coin has weight and maybe width, correct? We will use the width and the weight to cluster it into maybe 3, 4 clusters, according to how many weights, how many different coins you have. So you will cluster it, and after that, someone who will just look into it. Okay, this one it's more heavy and wider, so this one will be 20 krona. This one will be 10 krona. This one will be 5 krona. This one will be 1 krona. So it will be easy to give a label to each cluster. And in the future, if you got a new coin, don't know what coin is it, you will just weigh it, and you will measure the width, and you will say, okay, this one, it belongs to this cluster. It's closer to the center of this cluster. So we will say, okay, this one will be 20, this one will be 10, this one will be 1, this one will be 5. So this is the unsupervised problem. So in fact, it's supervised problem can be solved as unsupervised problem. Yes, so I would like to maybe give you maybe 20 minutes to try to go to this link and try to check this Colab. Yes, Aspen?
Yeah, do you hear me?
Yes.
Hello?
I will increase the volume of my mic, just a minute. Yes?
Yeah, does this lecture last to 18 as the schedule says today, or?
Which lecture?
This one.
Yes.
Does it last to 18 today?
No. We will finish at 2. We will finish at 2 today. Yes.
Okay. Yeah. Thanks for answer.
Yeah, maybe we need maybe 4 hours, for example, and the rest of the time will be exercise and stuff like this.
Okay.
So do you have many things to do after 2?
No, it was just a question though.
No, but also today maybe it's sunny, warm. Maybe people will go for swimming. Yeah. So I will give you some time now to just go please to the link for this Colab and try to explore it. And I will upload at the same time. I will upload those 2 small data sets to Blackboard, so you can just download it and try to upload it into Colab and try to visualize it. Just to visualize it. You can work in Colab and you can work in MATLAB. So. So now if you can go to Blackboard, in the folder which called the datasets, you have two files, one called Iris and one called Salary. Just download it. And please, if you will work with MATLAB, it's fine. If you will work with Python, it's okay. Just upload it to Colab or to MATLAB and try to visualize it. So for Iris dataset, you have 4 features and 1 output. Just a plot, maybe you can just plot, for example, 3 in 3-dimensional space, or just 2 in 2-dimensional space. So you have 3 classes. You can just visualize the 3 classes using 2 inputs. For example, the first 2 inputs, 2 features, and the target feature, you can just visualize 3 classes in 3 different colors. For the salary data set, it's we have X and Y, so we have independent variables and dependent variables. You just plot it in X and Y. Scatter plot, for example, you just do it as a scatter plot. So you have this data set here. Maybe I need to reshare small part. Okay. So you have this Blackboard. So you have here in the data sets, you have Iris and you have Salary data set. So just upload it's this one CSV file. This one also it's a CSV file. So we just need to upload it and try to visualize it. I mean, visualizing the data is very important because it will help us to understand how the data look like, what kind of pre-processing do we need to do, for example. So it's very, very important to visualize it. I mean, the next part, we will take an introduction to a perceptron. We will study a perceptron today, and we will try to use it for solving some simple problems like AND and OR, and why it cannot solve other problems like XOR, for example. I mean, there are lots of examples. So in fact, it's a nice tool to use, Google Colab. So we just did that from yesterday. Okay. So you need to import some libraries. You just need to import those. It's connected, just importing. Okay, and this is the file, files.upload, because I need to upload my data file for salary, for example. So I'm just uploading it. We need to choose a file. It's salary data. And the plotting, so you just upload it, and you need to extract X and Y. So I have X, it is the first column, Y, it is the second column, and plot X against Y as a line. So now it's as a line. And you can see here, when number of years of experience increases as salary increases, correct? So, and when we fit it with a line, we need to fit it with a line, correct? So in this case, we can just find I don't know. No, I have some errors here. Yeah, so we have a line here. So we can fit the data with a line. So now you can see those data points. We have those data points. This one, it's outlier, correct? So this regression models, it's a problem in fact, because it's very sensitive to outliers. So anyway, we have a regression line. We have some data points. So those are the actual data points which we used for building this model. And now I can just use it for interpolation, for example. So for 0 years of experience, you should get this salary. If it's 1 year of experience, you will get this one. It was not exist, in fact, in the data set, and so on, until 10, for example. And if you want to extend the line in that direction, you will be able to, to find, to predict beyond the values which we have. So, don't worry about this. Just to start with this one. I want you to plot this one. I want you just plotting this one, just visualizing the data, how the data look like, and what is the difference between regression and the classification. Regression, we try to predict or regress. And in classifications, we need to classify. I have a data point and I want to classify it. Is it class 1, class 2, class 3, and so on. So for example, if you want to get a loan from the bank, it's a classification problem. It could be also a regression problem. Classification, because I can classify them into yes and no. It's a binary classification problem. And it's a regression because I can just make prediction how much he should get, for example, from the bank as a loan. Should we give him 5 million? Should we give him 10 million? So it's a regression problem. Because people ask for a number, and also we need to refine it. Should we give it? Should we increase it? Should we decrease it? Of course, a perceptron. We can use a perceptron for classification, and we can use a perceptron for regression as well. This regression model here, it's very simple. The equation of this one, it's just y equal mx plus c, correct? Y equal mx plus c. So we have two unknown parameters. Those unknown parameters are the slope of the line and the intersection with the y-axis. So when we have this line, I want to find this line. How can we find it? Straight line. So straight line is defined by the slope, correct, and the intersection with the y-axis. So we have only two parameters which we want to get. In a perceptron, we have a weight value and a bias, and it's the same, correct? So we have here one input. If we need to plot this model, yes, Kevin?
How do you upload? Like, as you use the file.upload method?
Yes. Files.upload method, yeah. And you use Panda, read, CSV, and this is the file name.
Do you have any possibility to upload this file so we can work on it along with you?
Yes, I put it in Blackboard. So just download. You mean this one?
Yeah, your salary data.
Yeah, salary data, it's uploaded to Blackboard.
Because I can't find it under code, or if that's where you're trying to put it.
Not code, but it's a file called datasets.
Oh yeah, but I mean like the Python script you're working on right now.
Okay. You want this one? Yeah, it's fine. Yeah. So I want, because I put it in GitHub, right?
You could probably do that too.
To GitHub?
Or you can just save as a standalone file and then just put it on Blackboard.
Okay. So it's an intelligent system, and I put it there, right? And I can save it also as a standalone file.
Can't you upload the notebook?
Yes, I will do it.
Yeah, but it's under file. There's upload notebook option.
This one?
Yeah, upload notebook. A little bit higher.
Yeah.
Higher up. Higher up.
Up.
Up. Up. Up.
Upload.
There. Yeah.
But I want to download it. Correct?
Yes. Can't you just share the link, for example? Can't you just share the link on top if you want to? On top of the page, you have the web
this one.
link.
Okay.
Yeah.
This link. Link copied. Okay. In the chat. I hope if you can open it. And just to try to refine it, and so we can have copies from what we do. We can just have the final copy and put it in GitHub, for example. So, okay, because I'm getting a request from. Okay, I guess it's better to just maybe it's better to download it.
Ibrahim, it's in the machine learning repository, not the intelligent system repository.
Okay, okay. So it's but you can just use both, no problem. Yeah. Okay, I uploaded it also to Blackboard. And also you can work with MATLAB. So if you want to work with MATLAB, you can just also try to upload Excel file to MATLAB and try to plot it. This one, in fact, it's just for, maybe we have some problems here. We try to find absolute error and absolute mean square error. I don't know what is the problem here. And as you can see here in this figure, for example, it's for iris dataset. We have betal, for example, we have here Sepal width and length. And we have three classes, in fact, red class, green, and the blue. And when we use Sepal width and the length, we have this kind of overlap. Do you see this overlap? This red cluster, it's okay, but the green and the blue, there are, I mean, there is kind of overlap between them. So it's really hard to differentiate between the green and the blue using Sepal width and length. But if you use two different features, for example, we use betal width and length, we have different, I mean, we have good separation between those two classes. So it's much easier, in fact. So if it is classification problem, clustering problem, I can just draw one line here. We can just draw one line to differentiate between this class and those two classes. And if we need to have three outputs, in this case, we need to decision line. We need one line here, and we need another line here. So in this case, we can use those two decision lines to differentiate between three classes. Because when you have two classes, we need one decision line. When we have three classes, we need two decision lines. So it's a number of classes minus one. So I will leave you to work a little bit with this. I mean, with this coding, and we can meet again after maybe 12:15, for example. So you can just take your lunch break, and we can meet 12:15 to start working on I mean, the second part, which is the perceptron. You have the code in you have the code. I mean, this file you have it in Blackboard. So I would like to show you something. I mean, plotting the data is very, very important. I mean, in machine learning, usually they said people should maybe use 60% of their time for data pre-processing, and the rest of the time will be used for building your model. So in fact, it's very, very important to spend the time. Don't worry about time. Spend the time to clean and fix your data set and try to visualize it before building your model. So when we look for this iris data set, we have here, I mean, in this graph, for example, we have two features. And if you can see here, we have a red cluster or class and the green and the blue ones. The green and the blue ones, they are overlapped. So it's a problem. So in fact, if we build a model here, it will be able to classify the red one, but for the green and the blue one, there will be lots of confusion, right? So it's a problem. And if we go to the other two features here, we have another two features. For those two features, it's much better, in fact. So we have two different clusters here. I mean, the green one and the blue one are separated much better. We don't have that much overlap. So in fact, if we use those two features, so just by plotting the data, we can realize that maybe we can solve the problem using those two features, and we will get better accuracy instead of using the four features. So it's one way for understanding how the system will work. Because when we look into the system here using those two features, betal width and the length, we can see that the green cluster or the green class, it's a big distance between this cluster and the other two clusters. And the green one and the blue one, they also have some little overlap here. It's a very, very small overlap. So we should expect if we build a model here, maybe we can get an accuracy maybe up to maybe 95%, 96%, correct? We will have some little confusion, very, very little confusion between the blue one and the green one using the two features. But maybe if we can use some feature extractions or some feature engineering techniques, maybe we can reach better accuracy. So plotting the data is very, very important. It will help you to understand many things before working on your model. And also we can decide what kind of model do we need. Is it possible to use a perceptron? Maybe we can use a perceptron if we need to classify it into two clusters or two classes. Feed-forward neural network, how many inputs? We have here up to 4 inputs. So if we will use the raw data, we have 4 columns, 4 features. So in this case, from the data set, we can understand that we will use a feed-forward neural network. It has 4 inputs. And how many outputs? We have 3 outputs because we have 3 classes. So and in between, how many hidden layers, how many nodes in each hidden layer, it's up to us to select. So in fact, the feed-forward neural network here, if we can, I mean, it's too much advanced because we need maybe after 1 week or 2 weeks, we will be working with the feed-forward neural network. But when you look into this model, when we look into our data set, we have 4 features, correct? And a target feature. The target feature, it's the classes or the labels. And we have 3 classes. So in this case, from this data file, we can understand that we have 4 inputs and we have 3 outputs. So from the data file, we can start constructing our model. Our model should have 3 inputs and 3 outputs. And from those 4 inputs, is it really important to use the 4 inputs? Maybe, maybe not. But when we visualize the data, we discovered that using betal width and length will give us much better results. So we have here clear distinction between green class and the blue class. So I can just draw a line here. I can draw one straight line here, and I can draw one straight line here, and then we will have very good accuracy. Maybe this accuracy will be 97, 98%. Because very few samples, very few examples are overlapping here. We have some little overlapping here, so we can count it. So because the data set, what is the size of the data set? I don't remember, in fact, maybe it's 150 or something. So in fact, very few cases where we have some kind of overlap. So some of those will be misclassified. We will have some misclassification here between the green and the blue ones, right? So in this case, I can just draw one straight line here, and I can draw one straight line here. I can build very, very simple model using those 2 features. But maybe if we can, for example, use one of those features with those 2 features, it will be in 3-dimensional space. And maybe when it's in 3-dimensional space, we can find a plane which you can separate those classes into two different classes, right? So maybe if it is in 3-dimensional space, we will get much better results. If it is in 4-dimensional space, maybe we will get much better results, but it will be hard for us to visualize. So we will come here to the point of dimensionality reduction. I have 4 inputs. Maybe those 4 inputs are not very important. I can apply principal component analysis, and from principal component analysis, I will get new features, new superior features, which will be helping us to solve the problem in much better way. So maybe I will use those 4 features and extract 2 new features, and I will use those 2 new features for solving the problem. Maybe we will get much better results, because from principal component analysis, we are getting superior features, which can be used for, which carry lots of information. Maybe the first principal component maybe carry 60-70% of the variations in my data set. The second one maybe carry 30% or 35%. So maybe the first two features, principal components, will carry maybe 95% of the information in my data set, and might be it's enough for my model. And if we will use BCA in fact, we will work with a reduced set of features, and then we will have more simpler model. And when it's simpler, it's easy to understand, it's easy to train. We need, in this case, we will need much less data, because when the model is more complex, it means it has more trainable parameters, and those parameters need more data to train, and so on. So it's much lots of fun when we try to simplify the data and try to select the most useful features for building our model. Yes. So I just you can work, but I mean after 2, for example, you can work with those examples. You can work in MATLAB and you can work in Python. Try to upload those data files and try to visualize it in 2-dimensional space, 3-dimensional space, and try to see how much information you can get by visualizing the data. Now I will move to the second part. If you have question, please just ask me. Otherwise, we will go for the second part. And the second part today, it will be perceptron. We want to know what is a perceptron. Okay, so we need to know what is a perceptron. What is a perceptron learning rule? Okay, so now we okay. Yes. So now we will go to the perceptron. The perceptron, it's the basic building block in artificial neural network. So we have this perceptron, this circle, small circle, and this circle, it has some inputs. I guess I have some question. Yes. Okay, I will check it after 2. I will check if my data set is the one which I uploaded is different. I will check it. But you can download it directly from UCI repository. You can just download this data file directly from there. But I will check it after after 2. So now we will start. In fact, maybe this is not. I just need to check to find the correct. Okay, perceptron. Okay, no problem. So we will start talking about a perceptron. The perceptron, it's the basic building block. So we just need to compare all time with expert system. Expert system, we agreed that the basic building block in an expert system, it's the rules. It's the rule base. I mean, the rule base, it consists of number of rules. Each rule is an if-then statement, correct? If-then statement. It has some inputs and some outputs, and then we will use those set of rules for making a decision. So the base of information or the base of knowledge in the expert system, it's rule. or if-then statement, correct? In case of artificial neural network, the basic building block is a perceptron. And the perceptron, it's a very, very simple one. It's like a regression model. So the regression model, we will have, we created, in this salary data set, for example, we created one straight line. And this straight line, it has an equation to describe it. We can describe this equation by the mean and the intersection with the y-axis. So in fact, if it is an equation, if we plot it in two-dimensional space, the independent variable is x and the dependent variable is y in y-axis, we can say that the equation will be y equal mx plus c. Y equal mx plus c. M is the slope of the line, and the c, it is the intersection with the y-axis. So you can now just plot just x and y and draw in a line, and you can find the slope of the line and the intersection with the y-axis. So we can find this equation. So the equation will be y equal mx plus c. In this salary data set, we used this line for regression, correct? In classification, we can use the same line, in fact, for also classification, because in classification also, we will create a line. This line has an equation, and this line has a slope and intersect with y-axis. So, so the decision line will be a line. But when it's a classification, we can just say classes which are above it will be positive, classes which below it will be negative or will be 0, for example. So you can just say, okay, this class is +1, this one is -1, or it's a +1 and a 0, for example. So we will have the decision line, but we will not use the decision line for regression. We will use the decision line for classification, and this is the same. So in fact, the perceptron originally, it should work for regression, not classification. But when it's a classification, we can just assume that all data points which are located above the line will belong to one class, and otherwise will belong to the other class, correct? So we will create a decision line or a regression line. The regression line, it's the line which will be used for to regress. We need to find what will happen in the future. We need to predict. So we can assume a value for x, and using this line, we can find the value of y. It's like salary. So after 10 years in job, how much money I should get? After 20 years, how much I should get? Just expand the line and try to predict or regress, correct? In classification, we will have the same line. So we will have exactly the same line. This line will have an equation. So the equation of the line, it will be the same, y equal mx plus c. So it has a slope and it has intersect with the y-axis. But in case of classification, all data points which are located above the line, it will be one class or one segment, correct, of the data. And all data points which are below it, it will be a different class. So this is the classification problem. So in fact, there is no difference at all between classification and regression. Both are the same. So in fact, here we simplify it by drawing this circle, and we have some inputs, correct? We have input A, B, and C, and its input is connected to this circle by a line, and this line has a weight value. So in fact, and we calculate here the summation of inputs. We calculate the summation of inputs. So it will be A multiplied by omega A plus B multiplied by omega B plus C multiplied by omega C. So this one will be the equation of the line. So we don't have bias here, so we don't have y intersect. So we just assume that the equation will be y equal mx, correct? Or m1x1 plus m2x2 plus m3x3, correct? So if you are working in two-dimensional space, y will be mx. If you are working if you have two inputs, in this case, y will be m1x1 plus m2x2, right? So this is the equation of the straight line. So in this part, today we will just try to talk about a perceptron and the perceptron learning rule. We will not go to feed-forward neural network, only perceptron and the perceptron learning rule. And we will try to take some examples and try to implement it to see if it is working or not. So, because we know that perceptron, it is a basic building block. So if we understand how perceptron works, we will understand the feed-forward. But feed-forward, it will be a bunch of perceptrons, and it will be very complex. So we just need to understand the basic things, and when it's complex, we don't care, right? We will just use it as it is. It will be collection of perceptrons we will use the optimizer to optimize our model parameters and just test it, and that is it. So the most important for us today is to understand what is a perceptron and what is a perceptron learning rule. So artificial neural network, in fact, it was inspired by central nervous system of human. It was built based on the simple processing elements that are connected together into a larger mesh. So in fact, artificial neural network, just a bunch of perceptrons in a mesh structure. So we have like layers and different layers, many layers connected together. These simple processing units, we call it nodes or neurons. So in fact, an artificial neural network, it consists of a mesh or a large mesh of simple units. Those simple units, we call them nodes or neurons. And each node, in fact, it's a perceptron. So the mathematical model of the neuron, it's a perceptron. And artificial neural network are modeled after the behavior of biological neurons in our brain. So when they understand how those neurons in our brain behave, they moved it into mathematics, and they built this mathematical model maybe in 1940 or something. So it's really very, very old. So the building blocks of neural network, it's those neurons, and this is the biological neuron. This one, it is a biological one. And this is the mathematical one. This is a model which we will use. And when you look into it, it's just similar. So we have this circle, and it has some inputs. It's the same here. We have this cell body, and the cell body has nucleus, and we have some connections to this cell body. They make some calculations here, and they send an electrical signal to this terminal, right? So in fact, it collects signals from different cells, make some simple processing here, and after that, it will send a new signal to other layers or other cells and so on. So, and in the model, it will be the same. We have this, this circle. We have some inputs, and we will have some processing here, and we will produce an output. So the output here, it will be a decision, correct? So I have some inputs here. Maybe I have pixels, correct? Maybe I have an image, and this image it has a cat, and I want to decide, is it a cat or a dog, correct? So I will have many inputs here. All those inputs will be pixel values, and we will have some processing here, and it will just make decision. It will say, okay, this one is a cat, this one is a dog. So maybe the output will be binary, it's 1 and 0. When it's 1, it's a cat. When it's 0, it's a dog. So this is very simple. It could be something much easier. For example, it could be my income, my age, my gender, and so on, right? And I want, should I get loan? Should I yes or no for a loan, for example, from a bank? It could be something like this one. Symptoms, my body temperature, my pressure, and so on. Corona, for example. Do you have corona or you don't have corona, for example? So it could be a decision-making process. So we will have inputs. Those inputs will come from different, maybe we got those inputs from sensors or from image, from a book, from a magazine. It's just the data, correct? And we have some processing unit here. We have many parameters, lots of parameters here, and we try to make a decision. So the problem here, how can we select those parameters? How can we select the combination of parameters to train to make this kind of mapping between inputs and outputs? So this is the task of the optimizer. So inside the artificial neuron or a perceptron, we have this one. It's wait, sum up, and activate. We have 3 steps. We have wait. We have some weights here. So I have inputs. Those inputs are connected through a weight. This weight value, it will amplify or attenuate. Correct? I have a signal. Maybe this signal is it important or should I attenuate or should I amplify? Correct? So for example, I have an exam and someone just texts me because we should go to play football, for example. So should I go or should I not go? Because I have an exam, maybe I will give this one a very, very small weight. So I try to just minimize its impact on me. Maybe someone else will just send me a book or try to study with me. So I try to simplify it. So those weight values, it will reflect the importance of each input. When it's 0.7, maybe it's okay. When it's 1.4, it's more important. So, which means the input which is connected to 1.4, it's more important than the rest because it's very, very important for this problem. So we try to give it more weight, right? You provide lots of information. For example, and or you are in an interview, for example, and you have lots of features, you are good in programming, you have A's in many courses. This is very important, so it will take high value. You don't know how to swim, for example, it's not very important because we are company. I don't care if you know swimming or not. It's a feature, of course. Maybe we can give it 10%, right? But programming, it could be 2.5. Knowledge in control systems and robotics, maybe it's 2.1, correct? Swimming, maybe it's 0.01, for example, because it's not important for the task which we are doing here. So the first part here, it's weight, and it's very simple. We have inputs, just multiply those inputs by those weight value. And in fact, in the training process, we try to find a good combination of those weights. So at the beginning, we start by initializing it by random values, right? Those weight values. So we can start by random values, maybe 0.2, 0.1, minus 1. Minus 0.09, for example, so just random numbers. And after that, we will try to adjust those weight values in a way to create a good mapping between inputs and outputs. So the model, in fact, at the end, those weights will be, this is the model, in fact. This is the model, those weight values. So we need to find a good combination to solve this problem, right? But imagine in that interview, you should be hired, as an engineer, for example, and someone crazy, he just said, okay, no, I don't care about his programming skills. I don't care about his knowledge in machine learning. No, I want him to be a good swimmer. So he will give more weight to swimming skills and he will get the job. So it's misclassification here. We will be a misclassification because maybe you need a job in somewhere else, in a swimming pool or, right, as a trainer, for example, but not as an engineer, for example. So this is so we need to select those weights to help us to create a good mapping between inputs and outputs. So after multiplying, so we'll multiply and sum. So just multiply and sum, right? And add a bias value here. So imagine this one it's x1, this one it's x2, this one it's x3, this one it's omega 1, omega 2, omega 3. So the summation will be as matrix multiplication, it will be omega x, or it will be just omega 1 x1 plus omega 2 x2 plus omega 3 x3, correct? Plus bias, plus b, bias value. So this is the equation, in fact. So I will just remove those, just ignore this one and this one. Imagine that we have only one input. When it's one input, it's called x, and we have a weight value here, it's called omega, and the bias called the b. So the equation of the line will be y equal omega x plus b. It's equation of a straight line, right? So if we have a single input, and only one value for weight here, it's omega, so it will be omega x plus b. Omega x plus b, or mx plus b, it's the same as the regression line, which we just have seen in the salary prediction problem. So it's a straight line. So in fact, the perceptron also, it creates a straight line if it is in two-dimensional space, right? If it is in three-dimensional space, it will try to create plane, right? So it will be more complex. So after summing up, we will just have omega x plus b, omega x plus b, and after that we will have an activation function. So this activation function, it could be soft, or hard, right? Soft max, they call it soft max. So softmax or hard limb, for example. So softmax function, it's like sigmoid, or it's a normalized exponential function. We call it softmax. So finally here we will have an activation function. So the activation function here, it will help us to, because I have an equation of the line, and if we need to make prediction, maybe we will just have a line, correct? But I need to know what is the output. I have the equation of the straight line. So the output here, I will apply it to the activation function, and the activation function, it will give me a number. This activation function, there are different types of activation functions. It could be softmax, and it could be hard limb. So softmax, which means the output will be a float number. It will be a number between 0 and 1 or -1 and 1, correct? So the output will be a number between 0 and 1, for example. When it's number between 0 and 1, we can use this one for regression, correct? I don't need class 0 and 1. I just, or probability, for example, it could be probability. So when the activation function, it's a softmax, the output will be a probability. So imagine that I have all my information here, and I'm waiting the bank to make decision if they will give me a loan or not. So it's yes, it's a binary classification problem, yes and no. So after putting all my information here, we will get a probability here. It could be 0.7. So 0.7, which means the probability to get a loan, it's 70%. It could be 90. It could be 0.9. 0.9 means 90%. It could be 0.3. So chances are 30% to get a loan, right? So if it is softmax, the output here will be probability. If it is hard limb, it will be just 0 and 1. So just yes or no. So if you want to make it as a probability, you can use this activation function. If you want to get just the decision yes and no binary decision, so yes and no, you can just use a hard limb function. So this is a perceptron. This is the perceptron. How can we implement it? It's simple. I have X, so you need to define the input as a vector. Weights will be also vector, has the same size of inputs. And the bias here, which is B or plus B, just take summation. You can just take the summation by vector multiplication. So multiply X by W, correct? When you multiply omega transpose times X, you will get a scalar value. Apply this value to the activation function, so you will get the probability, right? You will get probability, or you will get decision 0 and 1. So this is a whole process. I just mentioned this each input here, it gets scaled up or down. When we multiply inputs, I have some inputs here, right? And those inputs will be multiplied by a weight value. So if I have a number here, maybe it's 10. 10 times 1.4, it will be 14. So it's scaled up. So in fact, we amplify this input because we multiply it by a value greater than 1. And it could be also attenuated, correct? So if we multiply it, if I have 20 here and I multiplied it by 0.6, so it will be 12. So in fact, we attenuate the value coming in this signal. So scale up and down. So in fact, values, I mean the input values, when they are multiplied by the weight values that is assigned to it, to this particular input, so it will scale up and down, correct? It will go up and down. If a neuron has 3 inputs, then it has 3 weights that can be adjusted individually. We need to adjust each one by one, in fact. During the learning phase, the neural network can adjust the weights based on the error of the last test results. So in fact, we will go forward, we will calculate the error, and we will try to adjust those weights to minimize this error. So now we understand it. So now we have some inputs. Those inputs are multiplied by weights. Those weights, it will take any values. Those values, maybe it's greater than 1, it's less than 1, it's a negative, positive, right? And based on those numbers, the specific input will be maybe scaled up or down according to the weight value. And finally, the weight value will reflect the importance of this input for this problem, right? So if I want to get a loan, maybe the age is very important because they want to be sure that I have 25 years to pay back to the bank, for example, correct? So maybe age is more important than gender. They don't care if you are male or female because anyway you have to pay, correct? So maybe females are better in paying back, correct? So in this case, we need to select a good combinations of weights which help us to solve the problem. So all inputs will be scaled up and down based on the weight value. We will adjust those weight values in the learning process. So in the learning process, we will start by random values because I don't know. Maybe the problem is very complex and it's hard to I can find those combinations for simple problems. So for simple problems, we can find those combinations, but for more complex problems, we need to use an optimizer. So the optimizer will help us to don't get scared from an optimizer because for perceptron, we will use perceptron learning rule, and it's very, very, very simple. Very, very simple one. So next step, all signals are summed up. We'll just sum up all signals. So in the next step, the modified input signals are summed up to a single value. We need a scalar value, in fact. So all inputs are multiplied by weights and adding to the bias. So we have a scalar value. We have a single value. The offset is added to the sum. We added this offset or bias. This offset is called the bias. The neural network also adjusts the bias during the learning phase. The bias, we will deal with the bias as a weight value. So in the training process, we will give it an initial value, random value, and we will adjust it in the learning process. At the start, all the neurons have random weights and random bias. So we need to give all those parameters which we don't know. We don't know the value of those parameters. So we will initialize all those parameters by random values. At each learning iteration, weights and bias are gradually shifted so that the next result is a bit closer to the desired output. So we will shift it a little bit. We will adjust it step by step in each iteration to reach the desired output. And when we reach the desired output, the error will be 0. So we will stop. In this way, the neural network gradually moves toward a state where the desired pattern are learned. So maybe we will use several iterations until we are happy with the accuracy or the performance of our perceptron. Activation. Finally, the result of the neurons calculation is turned into an output signal. We need to provide the output. We need to send the output. So this is done by feeding the result to an activation function or transfer function. So we call it activation or transfer. Why transfer? Because it transfers those inputs into outputs, and we call it activation because the neural network will be activated. When the output is 1, for example, we can just say it's fired or activated. So if the activation level exceeds the threshold, the neurons fire. We have a threshold here, and when this number is greater than this one, the neural network will activate and it will produce an output. This is an example. It's the garden bugs classification problem. We have bugs. It's garden bugs. So we have ladybirds and caterpillars. It's like coins. So imagine it's coins, or anyway, we have those bugs, and we need to classify them. And of course, we can classify them maybe by size and weight, for example, if it is coins. But in this case, in fact, in this example, we have 2 features. We have length and width. Of course, if you are using machine learning, maybe you can just do it by color. If you are deep learning, you can collect images, and the domain expert, he will just say, okay, this one is ladybirds, this one ladybirds, this one ladybirds, this one bugs, this one it's a caterpillar, and so on. And we will use those images to train a deep learning model to make classification using images. So you will just put your mobile phone on it, and it will just say, okay, this is caterpillar, this one it's ladybird, correct? Using images. But in this case here, he make it more simple for us, and he measured the length and width of each bug. Caterpillars are longer, and ladybirds than ladybirds. So this one it's longer, maybe this one it's wider, right? So this one is longer, this one it's wider. So we will have those 2 features, and we will collect our data, and we will use the scatter plot to have this graph. So when we plot it, when we visualize it, we can see that we have 2 different classes. One class, red class, it's caterpillars, and the green one, which is ladybird. So it's 2 different classes. And in the future, I mean, I need to build a model to help us to solve this problem in the future. So I will use the data which we have collected so far for building a machine learning to make a decision in the future. So what is the decision? The decision, as I told you, it's a line. So we need to create a line to differentiate between those 2 groups or 2 clusters. So we need to find this line. And when we have this line, if we got a new bug in the future, I will measure its width and length, and I will put it in the graph here. So if it is below here, it will belong to this one. If it is above the line, it will belong to caterpillar. So this is the machine learning, in fact. So I have a data set, and this data set, it consists of some features. We call it input features, and the target features. The target feature will be labels. So you just measure it length and width, correct? And you just someone, he will just look into the length and width, and they will say, okay, this one is caterpillar, this one is ladybird, this one caterpillar, this one caterpillar, this one ladybird. So this is my data set. It's labeled data set. I will plot my data set. When we plot the two features, we can find that caterpillars are longer than ladybirds, so they will be located in that part. Ladybirds are wider, so it will be located in that section. So I have two different groups, two different clusters. So the machine learning, from machine learning, I want to build a model to make the decision in the future, because I don't know, maybe I will sell this model to a country where they don't have this kind of experience, and I want to help them to make decisions, to decide if this one is caterpillar or this one ladybird. So I will use the data set. I will visualize it, because when we visualize it, it will make my life easy, because when we plot it like this one, I will see that, okay, I just need a very simple model. I just need a decision line like this one, straight line. But maybe if you didn't plot it, maybe you will go for the most sophisticated machine deep learning models, which requires too much time and too much GPU power to train it, and the problem is much simpler. So visualizing your data set, it will make life much easier, in fact. So we first visualize the data, and after that I will just decide, okay, I just need a decision line. I need a straight line to make the decision. So we will plot this line. This is a line, and each line has an equation, and the equation has two parameters. Those two parameters are the slope of the line, which might be 1, and the intersection with the y-axis. Correct? So the intersection with the y-axis. So it will be maybe it will be something like maybe the slope 1, so anyway, and the intersection with y-axis will be some negative value here. So the line will be very simple. It will be y equal maybe it will be x minus 0.5. Correct? So this is the straight line. So I can find, in fact, the parameters of the model from the plot if the problem is easy to understand. But if it is complex, it will be hard, because we cannot work with line, and we need to generate a plane, right? So in this case, it will be more complex. So from this problem, we discovered that we have two clusters, the red cluster and the green cluster. We need to draw a decision line. We draw the decision line. This decision line, okay, I'm happy with this now because it's in the middle. You can shift the line here closer to this one or closer to this one, or you can put it in the middle, right? Of course, when it's in the middle, it will be much better. Why? Because I don't know. Maybe there is a cutter. Maybe it's in the future, I will get a ladybird, which is much wider. So in this case, if I put the line here, it will be misclassified as a ladybird, as a caterpillar. So if you got a ladybird in the future, if we draw this line here, so if we put this line here, what will happen? So maybe I will get a data point which is just here. It's a ladybird, but because the decision line is closer to this one, it will be misclassified as a caterpillar, and vice versa. Maybe I will put the line here. It will give me accuracy maybe 100%, for example. But maybe in the future, I will get a caterpillar, which is just here, which is here in that place. So if I put the line here, it will be misclassified as a ladybird, which is not correct. So in this case, it's much better to put the line in the middle. When it's in the middle, my model will be resistant to those kind of noise. Maybe it's noise, because I'm just measuring length and width. Maybe I have a problem in my measurements. I have little bit some noise. So maybe those noises will force one of those data points to be misclassified as another one. So it's much better to put this one in the middle, right? So, and this location is one. Of course, there are many models, lots of models. Maybe one will say, okay, I will use this model. It's okay, right? Maybe someone who will say, okay, I will use this model. Correct? Maybe this one. So it's up to you. This one, it's a very easy one, by the way, because this one, it's just f of x equal width, right? So if the width is greater than maybe 0.5, right here. No, it's sorry, this one it's no. In this case, this line equal length. So if this one it's x and y, this one is y. So we will set all x. We can just say it's y equal, for example, maybe this one it's 2. or 3, for example. And all data points which are above will be one class. All data points which will below, it will be another data point. So there are different types of decision lines. There are different types of decision line, and we should select the one which will give us the best results, right? This one will give us very good results in the training data set, but maybe in testing, it will have a problem with some noise. So if I have a little bit larger ladybird, it will be misclassified as caterpillar. And if I have a smaller or a shorter, for example, caterpillar, maybe it will be misclassified as a ladybird if we use a line like this one, correct? So this line, it will be very critical. But the best line, it will be the one which will extend or expand the distance, maximize the distance between the two classes, which is this one, right? So maybe this one, it's the best model. Why it's the best model? Because it tries to maximize the distance between the two classes. It maximizes the distance and divide the distance between the two classes. So maybe this one will be the best model, in fact. So this decision line, it has some parameters, and we need to find those parameters. Those parameters will be slope and the intersection with the y-axis. So if we want to go into mathematics, or just, I mean, McLauch-Betts model. This is one of the first early models of artificial neuron, and it was introduced by McLauch-Betts in 1934, and it's known as linear threshold gate. They call it linear threshold gate. It has some inputs. Those inputs are connected to the summing point by some weights. So we calculate the sum here. Remember, we have a bias. So you apply the summing point to this function. We call it linear threshold function. Linear threshold function. They call it hard limb, in fact. So in MATLAB, they call it hard limb. And this one is very simple. I have a threshold value here. This threshold value, maybe it's 0.5. So I will calculate the summation here. If the summation, for example, 0.4, so the output will be 0. If it is 0.6, the output will be 1. Correct? So we calculate the summation. So summation, it will be inputs multiplied by weights. We will apply this one to this function. If the summation is greater than or equal the threshold value, the output will be 1. Otherwise, it will be 0. Or you can just use sine function. So it will be the sine of the input. So if the input is positive, so the output will be +1. If it is negative, it will be -1. So if it is greater than 0, it will be 1. If it is less than 0, it will be -1, for example. I mean, activation function, you can invent your own activation function, in fact. You can invent your activation function. This is just an example, decision boundaries for AND and OR. I mean, do you know this AND truth table, for example, this AND gate? This AND gate, it has 2 inputs, right? It has 2 inputs and 1 output. So it's 0, 1, 0, 1, first input. The second, it's 0, 0, 1, 1. And the output will be 0, 0, 0, 1. So it will be 1 when both inputs are 1. So this is the AND gate. When it's OR, it will be 1 when 1 is 1 or both of them are 1. So it will be, the output will be 0, 1, 1, 1. So in fact, if we can look into this data as a data set, we have 2 features. We have 2 input features, x1 and x2, and we have target features or labels, which is the output. And if you want to plot it, I think it's okay. So this one, for example, this OR, for example, when it's 0 and 0, it's 0. When 0, it's okay. No, I guess it's mixed, correct? So it should be like this one, correct? So we have 2 inputs, right? We have 2 inputs, and we have labels. So when it's 0 and 0, it's 0. When it's 0, 1, 0, 1, it's 0. When it's 1, 0, it's 0. And when it's 1, 1, right? When it's 1, correct? So the white circle, it's 1. The black circle, it's 0. It's like white pixel and the black pixel, correct? So as you can see here, we need to we need to build a model to make classification. If I have two inputs, right? If I have two inputs, I need to decide, is the output will be 1 or 0. We have two classes. So the white circle and the black circle. The black circle, it's one class, and the white circle, it's another class. And if we need to classify it, we need to draw a decision line, and this decision line, will be used for making those classifications. So all points which will be above the line, it will be classified as 1, correct? And all points below the decision line, it will be zeros, right? This is very correct, because the equation of this line, in fact, it will be mx plus c equals 0. So any points, the output on the line, it will be 0. And it will be positive above it and the negative below it, correct? So for OR also, it will be the same. This is the data set. When it's 0 and 0, it's 0, it will be black. When it's 0, 1, 1, 0, and 1, 1, it will be white. So we have also here two classes, 1 class and 0 class. 1 class and 0 class, correct? So also this one, it's just a decision line. A straight line will be very okay for us to make good classification. So I just need to draw a line in the middle between those two classes. All classes above the line, it will be 1. All classes, all data points below it, it will be 0, right? So this is AND, this is OR. So what about the decision line? If I want to draw, we just need to use a perceptron for creating a model to classify it, right? We need to create a model or a perceptron. So the perceptron is easy. Just draw this circle. This circle will have two inputs, x1 and x2, and a bias. Each input is connected by a weight value omega1, and the bias it's connected by b, right? So in this case, we will calculate the summation, and we will apply it to the activation function, and we will make decision. So let us draw it. So this decision line, what will be the equation of this decision line? If this x is x1 and this one is x2, so the decision line would be omega1 x1 plus omega2 x2 plus b equals 0, right? So the decision line, why it's the output, in fact, why it's the output? You can just say it's the label, right? It's the label. We need to see is it the label is for any point. I have a point here. Is it 1 or 0? Right? So I have another point here. A point here. It should be 1 or 0. If it is above the line, it should be 1. If it is below it, it should be 0. So we can have this equation, and this equation, when we look into it, it has 3 unknown parameters. x1 and x2 are inputs. Omega1, omega2, and the bias are model parameters. We need to find a good combination of those parameters to solve this problem. I want my perceptron to generate this line, right? So this is a line. The slope is negative, as you can see here. It intersects with the y-axis at some point here. So we just need to find the slope of this line, or we need to find those model parameters, omega1, omega2, and b. You have the straight line. Very simple approach. Very, very simple approach is just to find those points, right? Because the line intersect here, it's in 3 divided by 2 and 0, and it's divided and intersect this axis in 0 and 3 over 2, 1.5. So I have, I guess also, we are mixing those two. This is for AND, this is for OR. Okay, just this one. It should be like this. So this one for OR, this one for AND, because the intersection here it will be half. The intersection here it will be half, right? So you just select 2 points, because the line here intersect here in 2 points. The line here intersect to the axis in 2 points. Use those 2 points to find some combinations of weights. So using those combinations, we can have the equation of the straight line, and it will be work for solving our problem. So the decision boundary for AND and OR, we find the component of the line, and we have combination of points. So we will use this one for in fact this one is end. Yeah, this one is end, but maybe this one is for or, correct? Yeah. And for XOR, we will just wait a little bit. So now please, if you have any questions, just let me know. And you can go to MATLAB, you can go to Python and start working. We need to implement it. So I will share with you my MATLAB screen. I want to share with you my screen. Where is my MATLAB?
Question.
Yes.
Is this it for the actual lecture for today and now going into live coding, or what's up?
Yes, we try to implement now for maybe we can talk about XOR, but we need to finish this one first. We need to implement we need to implement this perceptron, and after that we will see how much time left. So I want to share my screen. Okay. So we need in MATLAB or in Python, you can just do it in Colab, but please share your code with me, right? But first we will do it here in MATLAB first. So I need to build a perceptron. Okay. We need to implement a perceptron. To classify and, for example, right? Is it okay? Can you see my screen? Yes. Okay. So you just start working with me, please. So first, we need to see the data set. What is the data set? So the AND gate or the AND, it has inputs and it has outputs. So this one, it's something standard in so we need to define input data. The data consists of input features and a target feature. So we need to have our own data set. So we will have, this is the input. It's a 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. It's similar to the truth table, which we have seen before. And the target feature will be this one. So this is the input, and this is the output. So we have those inputs. So we have 2 inputs and 1 target feature. Oh, sorry, this is XOR. I don't want to change XOR. Okay, we will go to this one. It's for OR, for example. So we need to define our data. You just need to define your data set. Data set of AND or AND-like, right? Because we can use AND or AND-like, which means we can generate a data set looks like AND. So this is the input features, and this is a target feature, okay? By the way, this is OR. Yeah. So now we need to, what will be the model parameters? We have two inputs, right? So, so the model, can you draw? Can you draw, please? I don't know how can I need to find a way to write here, in fact, but I don't know how can I make it. Is it possible to write on the screen in Zoom?
There's a button called View Options, which has an option Annotate.
Oh, this one. Okay. Yes, I can see it. Yes. So in fact, I want to plot something like this one. Oh, sorry. Oh, sorry. I will just clean it. So do you see it?
Yeah.
So this is, and we have two inputs, right? So the first input, it will be x1. We will call it x1. Sorry. This one will be x2. And we will have here summation, whatever, we don't care. And the output will be just y. So we need to build something like this one. This one will have a weight omega1. This one will have a weight omega2. And also we will have here a bias value called B. Right? And the input here will be +1. So we need to implement this one, in fact. So the decision line here, because I need to draw a line. So the line will be omega1 x1 plus omega2 x2 plus B. Right? So how can we clean this one? How can we clean it? Okay. So now we will have our equations. The model parameters. We need to. What is the model first? Okay. We want to find model. Slope of line and a bias. So because we need to have this one. We need to have this equation. So y, or I can call it f of x because it's function of x, equal omega 1 times x1. I have two inputs. Plus omega 2 times x2 plus B. So we just need to have this one, right? So I have those parameters. I just maybe initialized or just selected from the graph. We will see I have those values, right? And this is the bias value. So the decision line will be like this one: omega x B plus B, omega transpose x plus B, right? Because this omega, it should be like this one. When this one transposed, it will be rho vector multiplied by x, and x is defined here as column, right? So when we multiply omega by x, we will get 4 values, right? When we multiply omega by x, we will get 4 values. We will try it here. So I just show you. So we got 4 values plus bias. Plus the bias, so we will run it and we will see how much output. So now we got those numbers, correct? So for each input, because we apply it one by one, so when we apply 0, 0, we will get this number. When we apply 0, 1, we will get this one. When we apply 1, 0, we will get this one. When we apply 1, 1, we will get this one. But what is the output? What is the target output? I want to get those outputs, right? I want to get 0, 1, 1, 1. This is the target one. And I want to predict those values. So we need to change these numbers into those numbers. How can we do this? By applying it to this function, to hard limb function. So the hard limb function, all positive values will be 1, all negative values will be zeros, correct? So just apply this function. So it will be 0, 0, 0, 1. Is it correct? No, it's not correct. This is not correct. Which means the weight values are not correct. So this combination is not correct, right? Because do you see, this is the output, but the output, in fact, which we should get is this one. So this number is correct, this number is correct, but this one is not correct. So if I have 4 data points, I have 2 correctly classified and 2 misclassified. So in fact, the accuracy of this model is 50%, right? So the accuracy of this model now it's 50%, which is not acceptable. So this combination is not correct. Can you select another combination? And remember, this one it's OR. This one it's OR data points. So the OR, I will plot it here. I will plot it here. So I have 2 inputs, x1 and x2. So the first one it's 0, 0, which is 0. So it will be black circle. And we have white circle at 0, 1, white circle at 1, 1, 1, 0, and white circle at 1, 1. So this is the data point. Oh, no, I cannot make it. Okay. So anyway, you cannot see it. Oh, it's strange. How does this one work?
Your camera is actually off to your left.
Uh-huh. Okay.
Yeah, that one.
Oh, sorry. I have a wrong camera from. So I just need to get another camera. Oh. So now it's a different camera. No, so I need to get this one. You see? So this is my data set. So this is OR. Correct? This is OR. So I need to draw a line like this one. This one will be my decision line, right? So we need to find the equation of this line. So we know the decision line will be, it will be omega 1 x1 plus omega 2 x2 plus b equals 0. We have two points here. It's a 0 and half, for example. So it will be half x2 plus b equals 0. This one, it will be half x1 plus b equals 0. We can just select value for b, for example. I can select b equal 1. So in this case, omega 1 equal omega 2 equal minus 2. So maybe I will try this. Okay, this one would be negative. This one will be negative. This one will be positive, right? In this case, I will run this section one more time. What happened? Okay, what? Omega. So still not working. So what is the combination? We need to go get it from the PowerPoint. Okay, 2 minus 1, 2 minus 1, 2 minus 1. Okay. So, okay. So now we can get it's 2 minus 1, 2 minus 1. So using this combination, we got the same numbers. So do you see it? So this is the output, and this is a target. So this is the output, and this is the target. So this combination is very good, right? So selecting omega 1 equal 2, and omega 2 equal 2, and the bias equal -1, it will help us to solve the problem correctly. And in this case, the accuracy is 100%. The accuracy is 100%. You can implement it in different ways, in fact. And this is the hard-limb function. So the hard-limb function is just simple. If the input is less than 0, the output will be 0. Otherwise, the output will be 1. So this is the hard-limb function. You can get it from MATLAB, or you can just write a small function to do it. So now we can do it. So can you repeat this one for AND, for example? We did it for OR. Can you do it for AND? So just please implement this one in your Python in Colab, for example, and share it with me, or you can, or just try to do it in MATLAB, and let me know if it is working with you. So now we have a decision line. We can use this decision line for classifying any XOR problem, or any OR problem, OR and AND problem. So we selected those omega 1 and omega 2 by hand, because we draw the problem, and we can just do it. Can you give me, please, any signals that you are working in coding? Okay, great. So just write the equation of, so we have inputs, we have input features, the target features, we have some weight values, we have bias. This is the equation of the decision line. And after that, we will apply this, the output, this scalar output, to the activation function. We will use hard-limb function. Sigmoid, in fact.
Ibrahim, isn't it signum function you want to use?
I searched for it, in fact.
No, it's signum, not signoid.
Okay, so I did a mistake. Not sigmoid?
Signum, I believe.
Oh, like this? No, sine. It's a sine. No, I'm not talking about sine function, right? This is a sine function. I'm looking for sigmoid and Gaussian functions and stuff like this. But I don't know. It's not working here. Why? Sigmoid function. So it's different types of activation functions. So we use the hard limb, but we should be able to use other functions as well. But anyway, sigmoid function, it's easy to implement because it's 1 divided by 1 by plus exponential minus x. So sigmoid function, if we can just, I mean, this is sigmoid function. It's 1 divided by 1 plus exponential minus x. Okay. I don't know. I don't remember. I forgot. Maybe is it? We don't have return, I guess. And do we have return in MATLAB? Should be like this, correct? Maybe it should be something like this one. Maybe you can just I don't know why it's not working. Oh, matrix dimension must agree. Yeah, because this one is not working for. Do we need to use it like? I don't know. Do we need to make it like this? I don't remember. When I'm not using things, I lose it. I think it should be like this. So, do we have any plot? Okay. No, maybe it's not -1 So this is a sigmoid function. So we can use this activation function, in fact, right? So we can use something like this one. So instead of using hard limit function, you can use something similar to this one. So in this case, the output will be probability, right? I mean, the output here, it's between 0 and 1. 1 when it's 100% probability, 0 when it's 0 probability, correct? So we can test all activation functions. So maybe you can take it like a homework, a small homework, for example, to try to plot all activation functions, right? Plot all activation functions. Sigmoid, for example. I mean, hard limb, of course, it's, so we can just say here, figure. You want to sample it. So do you see this is the difference between the hard limb function and the sigmoid function? So the red one, it's the hard limb function which we just used. So when you see it, I mean, of course, the threshold here equal 1, correct?
You're only showing the MATLAB programming window. You're not showing the plots you're getting out.
Okay. Maybe I just need to share on my screen. So now you have this function. Can you see it?
Yeah.
Mm-hmm. So you just need to go to those activation functions and find the equation of all activation functions and just implement and plot it and make comparison between all those activation functions. We have here something very important. Do you see ELU, RELU? Those are very, very important activation functions. RELU, it's very important because it's very, very useful in deep learning, in fact. Because when we will go into more details, we will discover the difference between RELU and sigmoid, right? So sigmoid, it's a function which function which can be differentiated. It's a very important differentiable function. And RELU, it's very good for something called vanishing gradient. So it will be helpful for something called vanishing gradient, because we are using gradient descent. And at some point, those errors will be very, very small values. And when it's small, we will not be able to update our weights. So it will be good, in fact, if we can just take like a home assignment, is that we need to plot those activation function and its first derivative. So we need to find sigmoid and its first derivative, tan H and its first derivative, ReLU, for example, and its first derivative, and just plot it. We need to make comparisons because it helps a lot. I mean, in deep learning, people try to avoid using those sigmoids and those stuff, and they try to use ReLU because ReLU is really very efficient and very good to solve this vanishing gradient problem. So we can take it like a home assignment. Plot all activation functions and their derivatives. And make comparison. It will be really very, very useful. So just Google it, and also in the book you have a table, in fact. So in the book we have a table of all activation functions. Even in the slides here we have number of this one. So we have hard limb function, symmetrical hard limb function, linear function. Maybe linear function we can use it in when we are trying to predict, correct? So when we predict, we use linear function. Situating linear function, symmetric situating linear function, log sigmoid. So maybe it's the one which I implemented, it's called the log sigmoid, and hyperbolic tangent, those tan H, hyperbolic tangent, and the positive linear, and so on. So there are many functions. We need to know what is the difference between hard limb and linear. What applications? Because in fact, when you build your system, you need to decide which activation function should I use. So if you are using a perceptron for prediction, I guess we should use linear function. We cannot use hard limb, because the hard limb's output will be 0 and 1. So I want to predict my salary after 10 years, it will be 0 and 1. It's not correct, right? And if you will use also sigmoid or log sigmoid, it will give you a probability, a number between 0 and 1. But if you want to use it for prediction, so in this case, maybe you can just use linear or situated linear, right? You can just use linear. Linear function is why it's as an input equal output, by the way. So this linear function, so the value which we calculate. So do you remember the equation for the salary data set y equal mx plus b? And when we use it for prediction, I just need to get y. Y equal mx plus b. X is the number of years, and m is the slope of the line. B it's the intersect with the y-axis. Y is the prediction. So I just need to get y. So in this case, we need to use linear function, because the linear function it's y equal x. Y equal x, right? So the output equals the input. So in this case, we can use this one for prediction. So please, we can have it as a home assignment. We need to plot all activation functions and their derivatives. We can try log sigmoid, correct? Sigmoid, or you can just call it log sigmoid. I will just call it sigmoid. Linear function, hard limb, correct? Linear function, linear log sigmoid, maybe a hyperbolic tangent, and ReLU, please, ReLU. ReLU. And try to see the difference. What is the difference? I mean, the linear function, do you see the ReLU? In fact, its part is linear and the other part is 0, right? So it's maximal between 0 and x. So the input is x, and the output will be maximum between 0 and x. So when the input is negative, the output will be 0, and when the input is x, the output will be just x. So in fact, the one which is very close to this ReLU, it's a linear function, right? It's called rectified linear unit. So so if we need to have a home assignment, I just okay. So we will have some small problems. So number one, we need to use we just did this activation function. We did this perceptron with R. You need to repeat it one more time. Perceptron for and or, right? Number two, we need to implement a perceptron for regression. So I will just use this salary problem, salary data set, right? So because last time, I mean, in the example which I show you, and I shared it with you already in Blackboard, we used a regression model. Can we use a perceptron for regression? We need to see this, how it will work, right? Number three, for example, we need to plot all activation functions and their derivatives. Okay, so I will upload it to Blackboard, so you know what kind of home assignment we need to do. And also, I will just copy it to okay. Anyway, I will upload it to Blackboard, and you see it now. So we will go back to the slides, because there is part which is very important. We need to cover it today if you will be working with those problems. So you have those transfer or activation function here. So linear, okay, I forgot. Okay, we have linear function here. So I can put it here also. Plot all activation functions and their derivatives and find possible applications. One in regression, for example, which one can be used in regression? Classification. Vanishing gradient problem, etc. So you need to do this. Those activation functions, I can just say sigmoid, linear function, hard limb, hyperbolic tangent, and rectified linear unit. I guess this one will be very good. So we will go to the slides one more time, because I want to talk about perceptron learning rule. It's only one line. You see this perceptron learning rule. In fact, this one. So in the implementation, in fact, do you see those lines? Perceptron learning rule. Because now when we use the perceptron for solving and or, for example, we try to find those parameters by ourselves. So just to try those kind of parameters and try to implement it. and to find a good decision line. But we need to learn it. We need to learn it from data. Because if the problem is a little bit more complex, it will be hard for us to find a good combination of parameters. So in this case, we need to use an optimizer called perceptron learning rule. And the perceptron learning rule, it's very, very simple. We will go forward, we will calculate, we have this perceptron, we apply inputs, we multiply inputs by weights and bias, we will apply to the activation functions, and we will calculate the output. You just call it predicted output, for example, or output. And we have another desired output, right? So we will have a target output and the actual one. We will subtract the target from the actual. We will calculate an error signal. We will use this error signal for updating the weights. So the new weights will be the old weights plus this error value multiplied by the input, right? So it's omega new equal omega old plus error multiplied by input. The same also for the bias. Bias equal new bias equal old bias plus error. And I'll just repeat this several times. Repeat this until error is greater than or equal 0. When it's negative, when it's 0, it will stop by itself. Because when it's 0, omega new will equal to omega old, b new will equal to b old when the error equals 0. So we just need to iterate until the error value becomes 0. And the error value here, it's positive. Omega equal omega plus error multiplied by the input. And the idea here, in fact, because it's a very linear relationship, in fact, I have inputs multiplied by weights and calculating the output. If the output is less than the target, what is the problem? So the error will be positive, correct? So if the value here, if the output here is less than the target, so the error will be positive. And when it's positive, it means that I want to increase this one. So we will use this one with its sign. It's positive, so I need to keep it positive. So I will increase the weights a little bit using this value of error. So I will just update the weights because the weights, number of weights equal to the number of inputs, right? So I will update the weight value by a portion from or part from the input. So I will just add this value of error multiplied by the input. So I will increase it a little bit, and I will repeat this process until the output equal to the target. When the output equal to the target, this value will be 0. And then when it's 0, no change, nothing will happen here, right? What will happen if it's negative? Yes, if the output here is larger than the target, in this case, the error will be negative. And then when it's negative, it means I need to decrease the weight value a little bit until the output equal to the target. So the sign here is positive, because we need to use a sign of the error all time. We need to keep it. So it will be plus E multiplied by input. And for the bias, it will be just error multiplied by 1. Because because the input to the bias is 1, plus 1. So it will be error multiplied by 1. So we need to implement this perceptron learning rule for example, for this OR, for example, right? So we did it now, but if we need to implement, so we need here to implement perceptron learning rule, right? To implement it here, we just need to follow this one. So need to initialize this one. It's the error value, for example. We just initialize it as a big value, correct? So I can just say it's it's equal 10, for example. Anyway, in a number, we need to use while. While error is what? While error is I don't know. I don't remember while loop in MATLAB. Can you check it, please? I don't know. Is it while? for example, while error. So first, I have my I need to calculate the output. So y will be omega x. Sorry, omega transpose multiplied by x plus b. But we need to initialize it, right? So omega equal. I just give it random values. It's those are the weights. So it will be 2 times 1. Is it correct? Can you? So now it's just random values. And also the bias will be rand. Just any random values. So it will be this value. I don't know why error what. Error is so anyway, this one will be omega x. Okay, so oh sorry, I have different x values here. So I have those values. We will apply hard limb. Correct? So now we have the output. So now we have those outputs. It's not correct, of course. So we will calculate the error. But the problem, I'm doing it for, I guess I should not do it for, maybe I need to do it for maybe 1 by 1, correct? Maybe I can find it from. I don't know where is my. I just opened many things. Okay, so while error is maybe it's greater than. We will just do it. So, but I don't know if we should make it because now I will have error values. So anyway, the error will be target minus y, right? So it will be like this one. So I have those error values. So I will use those error values for adjusting the weights. So omega should be omega plus error multiplied by, okay, we can do it in one step, error multiplied by input, by x. But of course, we should do it one input by one input. I mean, it's a problem. I don't know how can we make it in fact, but you can just try to do it like this one. So omega equal omega plus error multiplied by x, and the bias equal all the bias plus error. And we need to run this one until the error becomes 0. Okay. Okay, thank you very much, Rasmus. You just need, I mean, this is this one, it's the perceptron learning rule. So now we are implementing the perceptron learning rule. We just initialize the error by some big value and initialize the weights. We need to initialize the weights. The weights and the bias with some random values. And after that, we will run, this is my perceptron. This is the perceptron. And this is the perceptron learning rule. So we calculate the error, right? And we update the weights. And it's very straightforward. Omega nu equal omega old plus error multiplied by the input. And the bias equal bias plus error. And we will repeat this one until the error is, unless, I mean, as long as the error is greater than some threshold value, we will just, maybe it's absolute value. You can just do it as absolute value of error, would be much better, right? And we do it example by example. In fact, we do it example by example. So one example is making it better, one example making it bad, and we repeat this process until it's much better. So there are many ways for implementing it. In fact, you can do it example by example. You can do it by epoch. So we can calculate the error for the whole for the whole data set, and use this error for adjusting the weight only one time each iteration, right? So we can go iteration by iteration. In each iteration, we will use one example, adjust the weights, or we can do it by an epoch, for example, and use this error for adjusting the weights, right? So just please implement it and share your solution with me. So in this case, we can add in the home assignment. It's not a large home assignment, but it's like, so you need to implement perceptron for and or. You need to implement perceptron for regression using this salary data set. So now we can understand what is the difference. What is the difference between regression and the classification? So this one, it's classification problem, and of course I want you to implement perceptron learning rule. Perceptron learning rule, it's very simple, and it's important to automate the selection of parameters, because now we are selecting it by maybe by random, by expert. Some people are expert, so they can do it quickly. Maybe it will be harder for other people. If the problem is simple, we can do it manually, but we need to learn how to automate it using the optimizer. So we will use here perceptron learning rule as an optimizer. And after that, we need also to upload all activation functions, the sigmoid, linear, hard limb, hyperbolic 10, and rectified linear unit. But please remember, you need to upload the function and its derivative in the same graph. So it's very, very important, but because it will help us to understand many things. Remember, if you want to use perceptron for regression, so what is the activation function? So I will just write it. So in this case, use linear activation function. When we use linear activation function, we will get results which is quite similar to the regression model which I shared with you. Yes. I think today we are done with it. Next time we will start by the perceptron again quickly and try to maybe check those home assignments solutions. Please, when you solve it, try to share your solution with me. And next time we will start by talking about a perceptron learning rule. And after that, we will go to feed-forward the neural network. So it should be in 2 weeks or 3 weeks, we should study feed-forward the neural network, and we should be able also to implement error backpropagation algorithm. In this stage, we will after implementing our feed-forward neural network, for example, for MNIST dataset or Olfetti or whatever, we will start, working with data pre-processing. We want to experiment principal component analysis and so on, and understand also some tricks in machine learning and some terms which are very important in machine learning. So thank you very much for today, and please just let me know if you have any questions. I will upload this home assignment to Blackboard soon, and you have from today until next week. It's not a big assignment, but it's nice if you can solve it and share your solution with me. Any questions, please? Any questions? So, yes.
Do you prefer if you use MATLAB or Python, or is it just the same?
No, it doesn't matter for me. I know the class is divided in facts. So one part came from computer science, and usually they prefer to work with Python. It came from automation, and maybe some of them prefer to work with MATLAB. So it's okay for me. The most important is to get a solution which is running. This is the most important. And my advice to all people to start using Python, because if you will go into deep learning in the future, you have to do Python, because Python has lots of.
If you know both, you would recommend Python.
What?
If you know both, you would recommend Python.
Yes, yes. I recommend it for your future, in fact, because in your bachelor thesis, for example, you will be working with data. You need to use some of those libraries and tools. So it will be much better for you to use Python. But personally, because I came from automation, so I feel more comfortable with MATLAB. So, but sometimes we need to go outside our comfort zone and try to do things in the right way. So from the beginning, I feel that I recommend all people to start working with Python, and just train and work, because it's the same. It's similar to MATLAB. In fact, there is no big difference. And in addition to that, it has lots of libraries which can be used for deep learning in the future, if you want. But if you prefer to use MATLAB, just go ahead. And even if you want to work with a GPU in MATLAB, it's now possible. So both are okay. But usually people prefer MATLAB for prototyping. If you want to do things quickly, you can do it in MATLAB. But for long-term solutions, I guess you need to do Python. Yes, of course. But I didn't run it because I need to fix it maybe. So this is a while loop. I can copy it, and I can put also this this file, I will upload it to Blackboard, but we need to fix it to be sure that it's working. So, so you need to initialize, you know, just to give error any positive, large positive value, you need to initialize weights and bias, and you will run your perceptron into a while loop, right? In this while loop, it will calculate output each time, and after calculating the output, we will calculate the error, and we will use this error for adjusting the weight value and the bias. And to adjust it, it's quite simple. Just multiply error by input, by x. So error multiplied by x for weights, and the error multiplied by 1 for bias. The bias is very important in perceptron because it gives us more freedom. In fact, do you know the decision line which we created using weight values? Those weight values will control the slope of the line. So you can rotate the line, right? Correct. So imagine it's in two-dimensional space. When you change omega 1 and omega 2, you can change the slope of the line. So you can rotate the line. If you want to shift the line up and down, you need to have bias. If you don't have bias, this line will go through the origin. So if the bias equals 0, so this decision line will go to the origin, will go through the origin. And in this case, your capability for solving more complex problems, it will be tough. So having a bias is very, very important in a perceptron and in artificial neural network and in deep learning. The bias is very, very important. And the idea is here, in fact, we have weights, we have bias. I mean, any decision line will be, controlled by those parameters, weights and the bias. The weights will control the slope of the line, so we can rotate the line in our two-dimensional space. And using the bias, you can go up and down, correct? If the bias equals 0, the line will go through the origin, and you will lose some capability for solving complex problems. Maybe you can solve it but you need, in this case, you need to maybe normalize your data set to be sure it's just around the origin area, right? But if you just want to use it as it is, in this case, you need to have the bias with you. So you initialize weight, and you initialize the bias, and after that you will use a perceptron learning rule to adjust it. Please plot the error also. I mean, if you will run this while loop, I wish if you can plot the error function. We need to see the error, because this error, it is a summation of error in each epoch. We can plot the epoch against epoch, and the epoch, it's when we run this algorithm for 1 iterations for all my data set, we call it an epoch, right? We need to plot this value of error, and we should see that the error goes down, will go down with iterations. So if you run this for loop for 5-6 iterations, we should see that the error starts by high value, and after that it will go down step by step until it's 0. Yeah. So please, solve the home assignment and just enjoy the home assignment, in fact, and try to learn, those basic stuff. And next time we will have all those parts ready, so you can just use it from Blackbox. Yes. Any other questions? And please, if you prefer, if you feel that we need a classroom, just inform me, so we can talk to Gertz and Webion, for example, so they can help us to get a classroom. If you feel that it's important to have a classroom. Yes. Any other questions? Okay, so we can just stop here today, and we will meet again next week. So see all of you next week, and have a good week. And please keep me in touch. Keep in touch with me if you have any questions or if you have any comments. Thank you very much for today. Bye bye.